Hello, hello, and welcome to eBPF Summit 2020. It's Liz Rice, and I am speaking to you from London.
Hey everybody, I'm Duffy Cooley, and I'm speaking to you from San Francisco in California. I'm still learning a bunch about eBPF every day, and I'm really looking forward to learning a lot more about it over the next 2 days with all of you.
So, if you're watching this now, I guess it means you found us on YouTube where we're streaming live today and tomorrow. And if you haven't already done so, do join us on Slack. That is basically where everyone is going to be hanging out. So, the URL is here. Join Slack and then find the eBPF Summit channel where everyone will be discussing everything that's going on.
As we work through all of the amazing talks and presentations during the next 2 days, if you see things that are exciting to you or things that you've learned, feel free to tweet about it. Get the word, help us get the word out for these sorts of things. And when you do, the hashtag to be used is eBPF Summit.
All right, so we are all set to have a ton of fun and learn a huge amount from our speakers and from each other. We do want everyone to feel welcome, so please be kind to each other and be respectful. We do have a code of conduct. You'll find it pinned to the top of that eBPF Summit Slack channel. And if you have any concerns at all over the next couple of days, please get in touch with Beatriz Martinez. She's linked in that pinned message as well.
Now, our Slack is going to be like the main source of interactivity for this great virtual event, and I wanted to thank you for each of you for being here at this virtual event. So, since we want to make this as interactive as possible, as Liz said, please join the Slack and join the eBPF Summit channel. There's going to be a number of sessions today, from keynotes to lightning talks. In those sessions, please ask your questions inside the thread posted for that particular session. And as those questions come along, if you see one that's interesting to you, give it a thumbs up or some other emoji, and we will select that question to ask live at the end of a keynote. All of our speakers will be available in Slack to answer your questions, so if it doesn't get asked live, you should still be able to get an answer for what's happening.
So we have been absolutely blown away by the excitement about this summit. There's well over 3,000 of you who signed up. In fact, the slide that I put up that I prepared earlier today, it's already out of date. I know it's over 3,400 now. So thank you all for registering. We know that you're all located all around the world. So thank you for those of you who are with us watching live right now. Welcome to each and every one of you. We do really appreciate that you're taking time out of your day to be here with us. And, you know, it's another virtual conference. I'm sure we'd all love to be able to meet in person, and hopefully that will happen soon. The majority of you told us in registration that you're end users of eBPF projects, things like BCC, Cilium, and Falco. We've also got a significant proportion of you watching today who are contributors to those projects, or who are contributors to the underlying eBPF technology within operating systems like Linux and Windows. Also, welcome to the around a fifth of you who are students or working in academia.
We also asked you during registration whether you're interested in eBPF for networking, observability, or security. It seems like your interests are pretty evenly distributed across all three. In fact, 55% of you ticked all three boxes.
So we've got a fantastic lineup of content for you over the next 2 days. We've got over 50 speakers delivering keynotes and talks. And I want to shout out a big thank you to our review committee who rated CFP submissions and helped us build this amazing summit.
Today's keynotes are coming right up. So we're going to have 3 in the morning, and we're also going to have a couple more in the back half of the day when we get into the deploying eBPF section of the day. So the first one will be Thomas Graft, joining us from Isovalent, and he'll be talking about the state and future of eBPF. After that, we'll have Brendan Gregg from Netflix talking about getting started with eBPF observability. And then the final one for this morning will be Yana Dogan from AWS talking about eBPF and microservices observability. Later in the afternoon, we'll have Sebastian Duff, Anthony Camtois, and Joseph Samuel from Sky talking about how they leverage Cilium and eBPF in their clusters. And then we'll have Dave Thaler of Microsoft talking about eBPF for Windows.
And as well as all those wonderful keynotes, we've got some terrific sessions today. They're themed around observability and security and deploying on Kubernetes. We'll be covering some other topics tomorrow. Get the full schedule from the Sessionize mobile site. That's a really convenient way to not only see what's happening, you can also mark your favorite sessions that you don't want to miss.
So later this afternoon, we're also going to be doing a live solving session for the first challenge of the CTF. The CTF is a new thing this year. It's going to be eBPF based. And at 10:40, we're going to be doing a live solving session with Tabitha Sable, who will be hosting it. And she'll be joined by some of the people who wrote some of the tests. So that'll be pretty fun. The first challenge is already posted. So during the breaks or when you have some time, try to give it a go and see what you think. As soon as that session is being live solved, we'll see the next challenge be posted. So you'll have plenty of time to work through it for the next one. Please remember, as you're working through this process, not to post hints or give away anything during the challenge until the resolution is posted. So after the resolution is posted this afternoon, then perhaps we could be a little bit more open for it. And the reward for all of this is bragging rights among your peers. So I'm really glad. I'm really looking forward to seeing how many people really enjoy this.
I think that CTF, Capture the Flag, is going to be a lot of fun. And another thing that we thought would be fun is for you to show us some pictures of bees. We want you to draw bees, ask your family to draw bees, take photos of bees. I've got a few bees that I have around my house. This is my favorite little cuddly bee. I've also got this edible bee. I do not promise that this bee will still be with me by the end of today. May have disappeared. So yeah, take some pictures of bees, post them into Slack. We think that'll be lovely.
And finally, we think this is going to be a fantastic couple of days, but we want your feedback to make it even better. So look out for the survey, which will be posted in Slack.
So I think it's about time to get started. So it's my pleasure to welcome our first keynote speaker, who's going to be giving us an overview of the state and the future of eBPF. Don't forget, there will be a live Q&A after this session. So we'll be asking you to post your questions into Slack. You can post them during the talk. So please give a giant round of emoji applause to Isovalent's CTO and co-creator of the Cilium project, Thomas Graf.
All right, looks like we're live. Hello and good morning or good afternoon to everybody. My name is Thomas Graf. I'm CTO and co-founder of Isovalent, chair of the eBPF governing board of our newly created eBPF Foundation, and also one of the co-creators of Cilium. On behalf of the eBPF Foundation, I would like to welcome all of you to this year's eBPF Summit. It's absolutely amazing. I think at the time of this recording, we already had over 3,000 registrations for the summit. So I'm really looking forward for the next 2 days. I believe we'll hear from fantastic speakers. Given the explosive interest in eBPF, I figured it makes sense to cover its current state and then also offer an outlook into the future of eBPF. So we'll hear some predictions from my side on how I believe eBPF will evolve and what it will unlock and what it will change. But before we get into that, I would like to give a very warm thank you to Liz and Duffy for hosting us today and tomorrow. They're doing a fantastic job. All right, so there's no better way but to start off eBPF Summit than with fantastic news. Last week, we announced the formation of the eBPF Foundation. Facebook, Google, Isovalent, Microsoft, and Netflix, we've all come together as founding members to create the eBPF Foundation. It is part of the Linux Foundation and will enable even better collaboration between the various eBPF projects and also ensure eBPF itself can grow and expand to additional platforms. An example of this is the expansion to the Windows kernel, which we'll hear more about in one of the talks later on. As part of this foundation, we are establishing 2 boards. The eBPF governing board, which will take care of running the eBPF Foundation itself, and the eBPF steering committee. The steering committee will drive the vision of eBPF forward. It will provide technical guidance and also speak on behalf of the eBPF community. In the spirit of open source, the steering committee composes of people who have either created eBPF or heavily contributed to it over the course of the last few years. And this is something that we want to keep. We are a contribution-based foundation, and we want our boards to represent that. If you want to know more about the foundation, or if you're interested in joining, feel free to refer to the charter available at ebpf.io/charter. Before we dive into more where eBPF is today, I want to quickly look back and cover why we have created eBPF back in 2014. For those not familiar with my own personal background, I was, or I guess I still am, a Linux kernel developer in total for, I guess, almost 20 years now. How did the world of kernel development look like before eBPF stepped in and changed everything? Let's look at an example. When an application developer wanted a new feature, let's say to observe an application, the application developer would walk up to the kernel developer and ask, hey, kernel developer, please add this new feature to the Linux kernel because I need to observe my application. In this example, we're using observability, but it really applies to any feature in the Linux kernel that is exposed to user space and then consumed or used by end users. The kernel developer would come back and say, okay, just give me 1 year to convince the entire Linux kernel community that your change is good and needed for everybody. A year later, the kernel developer would eventually come back and say, okay, I'm done. The upstream Linux kernel now supports this. Cool, right? But not really enough for the majority of us. Most of us consume Linux via a Linux distribution. And the Linux distribution will ship a particular Linux kernel version. Linux distributions, in particular enterprise distributions, will not always ship the latest kernel version. So in reality, it will then take another 5 years or so before the Linux distribution would eventually get back to the application developer with, good news, our Linux distribution now ships a kernel version with the required feature that you asked for. Obviously, by the time the requirements of the application developer have completely changed. As a kernel developer, this was kind of the story of my life. I have experienced over and over again that, for example, modern application platforms such as Kubernetes or container runtimes be built on features, kernel features that are 10 or 20 years old. Obviously, these kernel features were not built with the requirements of such modern application platforms in mind. So it always felt like pushing a rectangle through a round hole. eBPF changes this. By making the kernel programmable, a feature requested by an application developer or somebody else can be implemented with eBPF and loaded into the kernel, allowing for on-demand or dynamic innovation. What used to take years can now be done in days. So instead of the kernel developer responding, it can be an eBPF developer responding, okay, the kernel can't do this yet, so let me quickly solve this with eBPF. And then a couple of days later, the eBPF developer can provide a solution and start iterating on the solution together with the application developer. And even better, deploying this new feature will not even involve rebooting machines or any other heavyweight operations. In a sense, this is what eBPF is about. It's allowing for a massive wave of new kernel or operating system level based innovation. And it's changing a fundamental formula that change or innovation that used to take years can now be done in days. And this is unlocking, this will enable completely new ecosystem of tooling. So where is eBPF today? This is what it enables. How is it used today? Before we dive into more concrete use cases, I wanted to quickly cover the overall landscape. So eBPF today is used in a variety of use cases and an entire landscape has formed. So before we dive into the very concrete, very specific use cases, let's look at the layers first to understand what depends on what and how does the overall stack look like. Most eBPF applications can be associated with one of the following high-level use cases: networking, security, and observability. One layer below the use cases, we have eBPF projects, which solve one or more of these use cases and provide solutions directly to end users. This includes projects such as BCC, Cilium, Falco, Catron, or BPF Trace. I've listed just a few. These are the major eBPF projects. There are many more that are either being created right now or already in production quality. Below that layer are a set of libraries or SDKs, which are typically used by the just mentioned projects. And these libraries bridge to the world of the eBPF runtime. The libraries are usually targeting one specific programming language and offer bindings. So there are projects that include eBPF bindings for Go, C, C++, Rust, and Python. And then on the lowest level, this is where the operating system lives. We have the eBPF runtime itself, the eBPF verifier, the just-in-time compiler, and also the helper API. We'll hear several talks throughout the summit that will dive into all of these different layers. When we talk about eBPF today, in particular in the context of the foundation, we refer to this entire stack. Okay, so let's look at some very concrete examples on how eBPF is used in real life today. These are just selected few, obviously not including everything, but one example for each high-level use case. All the way on the left, we see Facebook leveraging eBPF for load balancing and denial of service mitigation. This work has been open sourced under project Catron. Facebook engineers have spoken to Catron in last year's eBPF summit, and there's also several public talks available. The next example is Google Cloud using Cilium to add eBPF-based networking security, and various observability features to Google's managed Kubernetes platforms, GK and Antos. Google Cloud is not the only cloud provider using eBPF. It's one example. We actually have members of the Google team speaking at this summit as well. Netflix is using BCC and auto tooling for application tracing, profiling, and performance troubleshooting. We'll hear from Brendan Gregg in a bit on how to get started with eBPF observability using exactly this set of tools. Last but not least, we'll also hear from Apple at this summit on how they use eBPF and Falco for a variety of security use cases. So given this wide adoption, what is next? And so I want to dive into a set of predictions, and then we'll see in the future, we can see how accurate they have been. Maybe actually in 1 year from now at the next year's summit, we can come back and actually look at them together. So let's dive in. Prediction number 1. eBPF will make observability intelligent. eBPF has massively changed observability already, but I expect eBPF to make observability a lot more intelligent going forward. What I mean by this is that observability will stop just exporting samples or data and then rely on filtering later on. Instead, eBPF will allow making intelligent decisions using the programmability of eBPF on what should be exported or on what can be safely ignored as noise. In fact, Jana, in her keynote later on, will go into exactly these details in her keynote and why this is crucial, in particular while observing microservices architectures. Prediction number 2. The eBPF will be the SDN of the cloud-native edge and bridge cloud, on-premise, and edge. SDN, or software-defined networking, has completely transformed networking during the virtualization era. I believe that eBPF will be the SDN of the cloud-native edge. It is a perfect match to address challenges such as multi-cloud, bridging hybrid environments, or building meshes to the edge. eBPF is an ideal solution for networking challenges because of its programmability. It is equally well fitted to drive networking for pure cloud providers or for cloud environment usage, but can also implement traditional network protocols such as MPLS, BGP, and so on. It can do so while providing a consistent and coherent user experience. So I expect more end users, cloud providers to adopt eBPF, for example, by using Cilium to provide consistent network services in their respective environments, whether this is in cloud, whether this is a hybrid environment, whether this is a sealed, airtight on-premise environment. eBPF has the right tool set to implement or address the challenges for all of them. Prediction number 3, eBPF is the technology to win service mesh. Obviously a bold prediction, but it seems pretty obvious to me at this point. Service mesh is a great way to think about service connectivity, load balancing control, authentication, tracing, and so on. But the implementation with a sidecar-based data path, as presently used in most service mesh implementations, is far from ideal. It is inefficient and complex to operate. eBPF will provide the same or better control in the data path, while providing the actual service mesh end user experience that we're all looking for. So I expect eBPF to be one of the prominent data path layers for service meshes. Prediction number 4, eBPF will provide deeper context across layers for fundamentally better security. This is a pretty abstract prediction, so let me add some color to this. Security heavily depends on understanding the context. The more context you have when making a decision, the better position you have to make a good decision. This is no different with security. Understanding the identity and intent of actors, requests, and communication is crucial. eBPF will dramatically increase the available context when doing enforcement and also when providing visibility. So I think we'll see solutions that can combine context from the network level, process runtime level, and maybe even include information from the orchestration system level, and then take all of that into account when enforcing actions, including, for example, feeding from real-time based historical context views. In parallel, eBPF will allow achieving this better security model at a low overhead, which I think is crucial as well. Prediction number 5. I think this is one of the important ones. eBPF will make having observability everywhere the norm. Whenever I talk to users or customers, having observability is one of the most requested asks, whether it is understanding the application performance, request latencies, security compliance metrics, or network visibility. Having visibility is absolutely key. It's frightening how little of observability is available in many environments. eBPF will change this and make it the norm to have visibility across all these layers. Why? The main 2 reasons why observability is not available today are lack of opportunity, so not having the opportunity to see what's going on, or imposed overhead. eBPF solves both of these challenges. eBPF, because it lives in the operating system level, can see everything from low-level networking on the wire to runtime system calls, what's going on in the kernel, all the way into instrumenting applications, function tracing, or even parsing application protocol requests. It can do so with a very low overhead. This connects back to the intelligent observability prediction that I made earlier. If we can make more intelligent decisions on what to observe, what to capture, the overhead will be lower on the overall system. All right, last prediction, final prediction. eBPF will allow for networking, observability, and security tooling with an amazing user experience. Okay, this is very generic, but I think it's the most important prediction overall because it connects everything together. In the end, everything we are doing, everything we're building for users and customers. And we're optimizing for our users to have a good and amazing user experience. Whether it's solutions to provide network security, application request tracing, runtime security, threat prevention, or monitoring systems, the quick innovation cycle that eBPF unlocks will allow us to interact with users quickly and interact with them. This will lead to a fundamentally better user experience for all of us with the eBPF tooling that we're building together. All right, that's all the predictions. I really hope you enjoyed this talk, and I hope you were able to extract some useful information from it. I'm really excited about eBPF and the future it has ahead. And with this, I would like to say thank you and open it up for questions.
Thank you so much, Thomas. That was a really great talk. And I think I'm speaking for everyone to say we're really excited about the eBPF Foundation. So thank you for describing that to us. So we got a few questions came in on Slack. The first question is asking, BPF features are slow to actually get into distributions. So are there any plans to speed the way these features get into the distributions?
Yeah, I think the best plan there is to just keep pushing eBPF in general, and the more demand, the more likely distributions will backport particular helpers into distributions. But then I think what's important is that the entire goal of eBPF is to not require additional helpers all the time, but basically work with the existing helpers and create innovation that way. So yes, I think the more demand we see for eBPF, the more incentive distributions will have to backport. At the same time, I think we already have a great set of helpers that don't need to be expanded constantly.
Another question from Brian Lee: can we build drivers in BPF?
Yes, absolutely. I think it's not the main purpose of eBPF. I think in general, I think eBPF is designed and made to build logic, glue, kind of the intelligence to connect various kernel subsystems together or extract visibility and so on. But there are several examples where drivers have been written in some way. I think there has been some radio frequency driver stuff in the kernel that's been done in eBPF. So I think yes, in theory, yes, but it's definitely not one of the main purposes. But if you have a side project, if you want to dive deeper into eBPF, like looking at implementing a driver in eBPF is definitely one of the nice options you have.
We're getting tons of questions coming in. There was quite a funny one though that came in while we were speaking earlier. Where is Martin Casado?
I guess I'm assuming this is referring back to the SDN prediction that I made. So yes, Martin is actually an investor into our company, Isovalent. So he definitely very much approves of eBPF. He's a big believer. He actually also wrote a blog on why Martin believes eBPF is the future of networking and why eBPF kind of completes the original vision that Martin had for SDN. So if you are into SDN, if you are interested in Martin's standpoint, I can post the link to that blog post. He's definitely a big believer. Otherwise, he would not have invested into our company.
Another question came in, a bit more of a pretty serious question. How can eBPF provide, in quotes, better security when it has a track record of vulnerabilities in the Linux kernel? Yes, Matthias Krauser asking about this, saying that it's been disabled by default for unprivileged users.
Yes, so I think that's actually the key. It's important to understand that from a security perspective, eBPF can be operated in two ways, as unprivileged or privileged user. In general, I would advise that if you're running any type of production system, please do disable privileged eBPF. Reserve the right to use eBPF for privileged processes. And at that point, I think the majority of attack vectors will disappear with eBPF. The main purpose of unprivileged eBPF is to allow, for example, some application profiling use cases, some traffic steering at socket level, but it's relatively limited. So unless you have a real use case, please disable unprivileged eBPF. And I think the second point there is it's actually expected that as a technology gets more widely adopted, there will be a stream of security issues found. And that's actually a positive signal. No software is bug-free, obviously. So we're seeing the same thing with Kubernetes or Envoy or other projects that have gained popularity. As something gets popular, lots of eyes are on it, and security issues will be found. Maybe the last piece here is, I think the reason why below the line it's a positive formula in the end is, I think, eBPF is capable of observing the entire system. So it's actually doable to observe eBPF with eBPF itself. So yes, there are certain exploits that have been done, for example, using the eBPF system call, but you can use eBPF to prevent that as well. So eBPF itself, I think, is a framework, is a layer that will establish a lot of new use cases, including enhanced security, but you need to make sure that you still harden your system, and this includes disabling unprivileged eBPF as well. I hope this was answering the question. It's a relatively complicated topic, so I'm happy to follow up on Slack and have a deeper conversation as well.
There have actually been tons of questions coming in. I think particularly reacting to your predictions, it's given a lot of people a lot of things to think about. So you're going to have your work cut out for you answering questions in Slack. But we are out of time for now. Thank you so much, Thomas, for your talk, and good luck answering all the questions that are waiting for you.
All right. Thank you very much.
Awesome. Thank you so much, Liz and Thomas, for that amazing keynote and for the Q&A section. You've all done a wonderful job of asking questions in the Slack. Please keep them coming. And now it is my honor to introduce our next keynote speaker, Brendan Gregg.
G'day, my name is Brendan Gregg. Welcome to the eBPF Summit 2021, and I'm joining from Sydney, Australia. In this keynote, I'll share how to get started finding performance wins using eBPF. I shared a similar keynote for the first eBPF Summit, but eBPF is a changing and evolving space, so it's important for me to share updates. Now, for a lot of other technologies, if you want to get started, you can do an internet search and click on the first how-to guide. But because eBPF has been changing, an internet search will uncover many documents that used to be true back in 2015, but are no longer so true today. Many of these documents get you to start by programming BPF using the Python BCC interface, for example. But that's not really how we want you to get started today for performance wins. I've decorated this screenshot with the first article is not for beginners, the third article is not the best start, and so on. Also, if you do a search for BPF, you'll find many explanations of the acronym that are also dated. So nowadays, BPF is a technology name and no longer an acronym. BPF itself is a bytecode and execution environment that we're using to create observability, networking, security, and other software. So how do you get quick and easy BPF performance wins? It's to think like a sysadmin and not like a programmer. I used to be a system administrator at the start of my career, and my job was to make sure that all the required software was installed in our systems and worked. And nowadays, there are two great collections of BPF performance tools you can install. There's BCC and BPF Trace. And so you can install them and immediately start using that software and get performance wins without having to start by writing code. Those are the commands on the slide, and I've highlighted the top 5 commands you can try. And you'll find these are quite useful. You might unearth some performance wins just from this one slide. So the first command, exec snoop, that's going to show you which processes are running or firing. And you might discover you have some background shell script that's calling things and perturbing your application that you've forgotten about, or something's launching out of crontab. The second command, open snoop, that's great for debugging misconfigurations, like when an application is trying to read a log file that's missing or configuration file that's missing. TCP Live is great for seeing the flows of TCP connections around your environment. And so it will show the bytes transferred and durations and the IP addresses and so on. You might discover some unexpected TCP sessions or misconfigurations there as well. ext4 slower shows file system performance. And that's a more direct measure of performance than looking at disk metrics. And so straight away, you may be able to eliminate the I/O stack by looking at how the file system is returning I/O and the latency there. And then to drill down into the I/O stack, BioSnoop shows you the disk access pattern, and you might discover issues there as well, such as outliers. So that's just 5 tools. You can just run them as is, and you might find some performance wins straight away. I'll share a case study of how these fit together, and this is from something I analyzed. This was a Cassandra database, and I begin by using the standard Linux tools like IOStat, and I saw that the disk utilization was around 15%. So this is a light workload, and I've got around 5 milliseconds for the average wait time. It doesn't look like a disk issue, But I know that averages, such as what these metrics and also what monitoring UIs show you, can be misleading. So before I rule out disks, I'd like to see a bit more information, and there's canned tools for that, like BioSnoop. So I run BioSnoop, and wow, Perl is doing all this disk I/O. So Cassandra is a Java application. It's not a Perl application. So something is amiss. Actually, if you think about it at Netflix, if you find a Perl program going amiss, there's a good chance that I wrote it, since I love Perl. But there's only a few of us at Netflix who do and write software in it. So there's a good chance this is one of my own programs that's misbehaving. So what is it? Back to Unix tools, ps-ef, pipe grep Perl, and I see it's our log rotation service. And there should only be one copy of those. It has gone haywire and it's launched a dozen of them. And so that's an issue, and so we can fix it. And the Perl programs themselves were going haywire with this log rotation and ultimately causing disk I/O that was perturbing the Cassandra database. So, quick and easy performance win, and it's just including one of these new tools as part of your regular diagnosis toolset. IOStat, BioSnoop, ps-ef, and so on. And there's many other tools for getting more information from the system. Here's a diagram I've drawn of them where I've shown a generic kernel and operating system. And in black, a lot of the tools that come from BCC. And so you can apt-get install the BCC tools. In red are new tools I've been developing for my BPF book. And they're all open source. They're written using BPF trace. And my goal when I create a lot of these tools is so that you can solve more than 90% of performance issues using the canned observability tools, the tracing tools. If you need to write custom tools, you can do that too. When we talk about why BPF observability is awesome, this is why BPF observability is awesome. It's because all of these tools were created out of necessity, and they show metrics and insight that you can't get from the other tools. So BPF observability, it's not about coding this and that in the virtual machine. It's about this. It's about solving actual issues for your company. So whenever some people talk to me about why BPF observability, why should we care, it comes back to this diagram. It's so important. I put it on the cover of my book because this is why it matters. I also printed out and used to have it on my office wall. I've since moved offices. I need to put up a new one. And I use it as a checklist. You can, if you know you've got an issue, say in the block devices or disks, you can then go around and see which of those tools, canned tools, exist and see what sort of insights they provide. I can look at the SCSI level, latencies. I can look at disk errors. I can look at the patterns of access and so on. And also, you can walk up the stack. In this case, the IO stack has the application system calls, VFS file systems, volume manager, and so on. I can walk up the stack and try all of these tools to really understand the performance of that IO from different layers. Now, that's great that we have all these tools and we can run them, but I think the future of BPF performance observability is really GUIs. At Netflix, we have hundreds of thousands of instances, and it's not easy to just log into a whole heap of them and try to debug performance. Which one do I log into? And if I pick one, then am I sure I'm on the right one that's causing outliers, or did I miss it? It's critical that we have user interfaces or GUIs that scale so that we can look at the cloud as a whole or applications as a whole. And ultimately, it will be the same with the new BPF observability sources that we've created. You will have a user interface, a GUI on top of it. Susie at Netflix has been creating one so we can click on CPU report and then it runs the CPU tools. So you get all that extra information you don't normally get out of monitoring. And there's different reports for different types of resources. It's using the open source tool, so it's built right on top of those BCC tools and BPF trace tools. And so as they get updated, we're getting the latest metrics. How do you fit this together? I've got an example diagram. So this is how we used to build it at Netflix. This is Netflix Vector, which we've now retired. But we had a web server that had the GUI web page, which is the dashboard interface. The client would load it, and then it would connect to instance agents, and we were using Performance Copilot, PCP, and those instant agents would launch BCC tools and then send the data back to the client GUI. And so that worked. It meant installing BCC on all of the servers. We're now doing a new one called Flame Commander. It's part of Flame Commander. Flame Commander does a bunch of things, cloud-wide profiling as well, and differentials. This one, the web server itself has the BPF trace tools, and then they get pushed out to the servers to run them. And that's great because we can update the BPF trace tools and customize them in one place, and then push them out and everyone's running the latest. Note that I don't have persistence in here. You can add a service so that you record data over the time. So this is just a simple model so that you can look at live metrics. So think like a sysadmin. Start by trying out these BCC and BPF trace tools and use them as is, fetch updates. If you look at them, some of them look deceptively simple. They may only be 100 lines of code. And I know sometimes when people get started with building upon BPF observability, they look at the tools and think, well, I'm just going to rewrite these in my own language. I would try not to do that because there are frequent updates. And it's because these are not the same as other types of software. A lot of these tools are instrumenting kernel, application, and library internals using dynamic instrumentation, which instruments the raw code. And that can change between versions. And so many of these tools require ongoing maintenance to match kernel changes. And so you don't want to inherit that burden. If you rewrite these tools, which you can do, you will then have the burden of having to update them all the time. If you can, try to use the upstream versions like we're doing at Netflix. And those upstream versions, the BCC and BPF trace tools, they are updated by the BPF engineers at Netflix, Facebook, Isovalent, and many more. So they're really the best. They're the standard tools. Now, sysadmins do sometimes program, and that will be the case here as well. So if you think about shell scripting awk and sed one-liners, how that looks for performance observability is BPF trace tools and BPF trace one-liners. So you will think like a programmer if you have a real-world problem that the tools don't solve. So you've tried the CAN tools, you need to go deeper into some weird part of an application or library or kernel, you can create a new tool. BPF trace is a great way to start. If you're a BPF-based startup, you may have greater needs of BPF and you want to go into programming. If you're debugging your own code, you need custom things. Or you're doing networking and security. Things that aren't performance observability don't necessarily have all the CAN tools. So, I mean, there are things out there for containers and other things as well. Or if you really want to learn BPF internals. So there are reasons to think like a programmer. But if it's performance observability, start with the CAN tools and see how far you get. The recommended tracing front ends, just to run some tools, BCC and BPF trace. If you want to hack up some new tools, BPF trace, it's like awk. It's very simple, it's easy to pick up. And if you want to spend weeks developing a BPF product, then BCC libbpfc, that's the new interface we're using. It's lightweight, it has compile once run everywhere, and the BPF type format based kernel information. BCC Python interface is now becoming the obsolete interface. It requires LLVM. It's special use only these days. But there's also GoBPF and the libbpf RS Rust wrappers. If it seems like there's too many front ends, it's similar with Unix. So if you want to run some tools, there's a lot of CAN tools in user bin. If you want to hack up some new tools, that's shell scripting, bash or awk. And if you want to develop products, then you'll be doing C and C++. As an example of BPF trace, I've mentioned it. Here's a tool that I wanted to write for a long time, Read Ahead. and it shows the read ahead. This is for the file system read ahead, and is read ahead working or not? This is something I wanted to answer. So what I'm doing is I'm showing if we read information or if we read data from files, how soon did we use it? If we used it pretty soon, it meant read ahead was doing what it's supposed to do. If it sat in the cache for seconds or minutes before it was used, read ahead may be too aggressive and need to be tuned. So this is great that I can just come up with this new tool and see the information I want to understand read ahead tuning. And what's great about BPF Trace is the entire tool fits on one slide. Now I mentioned libBPF as well, so that's a new interface in BCC, and so it's using the latest core and BTF. With it, you can write tools that have the BPF code embedded in them, and so they do not require heavyweight LLVM or Clang dependencies. This makes them great for, say, embedded environments or space-constrained environments. And also in the future, we'll be able to just have a package of these lightweight tools, like 100 kilobyte tools that are completely standalone that you install, and then you get OpenSnoop and TCP Life and whatnot. Just as an important announcement, make sure to support the future of BPF, you have the config debug info BTF is set, and so lots of distros are now setting that. So the future for BPF in general is these event-based applications where you have user mode applications and then kernel mode applications where an event triggers them and they're running in that BPF virtual machine or sandbox environment. And it's really a new type of software. And I've drawn this table to show you the differences between BPF and user and kernel. And we have some of the best of both world attributes. So with BPF, it can be user-defined. So at the shell, I can create new BPF programs and run them, whereas at the kernel, it's much more complicated. But with BPF, I also get better device access. Not as good as the kernel, not completely direct, but I have these restricted helpers that run in kernel space, so I have much faster access to devices. So I can write high-performance software. And there are various other advantages over kernel software as well. So the takeaway, to get started with BPF performance wins, think like a sysadmin, install BCC and the BPF Trace tools, run them, get some wins, then later on try programming if you like, but get some wins first, save your company millions, and everyone will love eBPF. I have some references in the slide, and I cover BPF in my last 2 books. And thank you very much. And thanks everyone for building BPF and the front ends.
Awesome. Thank you very much for that presentation, Brendan. And I think I speak for all of us when I say thank you for all that you do to further eBPF in this community. So we have a few questions that we have. Yeah. So we have a few questions that people have asked here. Let me dig into them. The first one is, what are you looking forward to in BPF observability?
What I'm really looking forward to is seeing people use it to find performance wins. I'm looking forward to seeing the blog posts, the meetup talks, where people say, I used this, I saved my company $1 million. These tools were really helpful. A lot of us in BPF, we've spent years and years creating these tools, and we've had a preview of how useful they are. So I've used them for various performance wins at Netflix, but I'm really looking forward to seeing that for other companies as well, and people continuing to take it further. And so I've given many talks on what BPF is and how things work internally and how the tools work, but I'm really looking forward to seeing people use it. I feel I've talked quite a lot about building it, and now it's time to use it.
I like it. The next question we have is, I understand the single node observability that, Sung mentioned that they understand the single node observability that you had, that described the image that you had posted in your presentation. And the question is, how about eBPF with distributed tracing framework? Any plan to connect eBPF with OpenTelemetry, for example? Have you seen folks exploring that space?
I have seen people looking at it, and this is how we'll see things emerge in the future. At the moment, if you look at the workflow of how we use BPF at Netflix, we already have a distributed tracer. We're based on Zipkin. We have cloud-wide monitoring using our own tool, Atlas. And they're great at looking at common performance issues. So we make sure we have metrics for those common performance issues. And then when we have weird things, we're drilling down into a microservice. We're drilling down into some sample instances. And that's when we bring up the per instance tools and we're firing up the tools themselves. So and a lot of the examples, I understand a lot of the examples I show, here's one bad instance and I'm debugging one bad instance. That's the workflow we do at Netflix. If we get to the point where I'm using a tool to look at a metric that should be cloud-wide across all instances, then sometimes it's a case where we want to change the kernel and just make that something out of proc or something that the kernel's providing 24/7. BPF is, if it's such a common use case, we don't have to use BPF for absolutely everything. BPF is great for prototyping what can become new metrics in the future. And so, yeah, I mean, we will use BPF, but in the longer term, if it's just the 24/7 monitoring metrics, we'd bake them in.
Nice. One of the questions I actually, as I've been learning about eBPF, one of the efforts that I've seen really taking off is this effort around compile once, run everywhere, which is a pretty interesting. And you referred to it in your presentation when you were talking about like config, debug, BTF, and how you can actually make those types available inside of your running kernel. Like, how do you see that changing the work that you're doing around observability in that sort of space?
No, this is really fantastic work, and thanks to the Facebook and other engineers who got this going, also at Isovalent. So it's been great to use at Netflix. We've got BCC and BPF trace in our base AMI, so they're installed on all our instances. And if there's a performance issue, I can just log in, I can run the tools. It's great. However, for other companies and other environments, it's more resource constrained. And historically, BCC and BPF trace needed the LLVM libraries. So the compile once run everywhere, coupled with BTF, mean we can compile these performance tools as what may be 100 kilobyte standalone binaries. And there's already been a lot of volunteers who have been porting my tools over to the new C interface. And so in the future, instead of telling people apt-get install BCC, BPF CC tools, or whatever the distro decides to call it, you'll be able to, we'll have a new package, I assume, which will be, say, BCC-binary tools. And so you do apt-get install BCC-binary tools. There's no dependencies. It could be like the top 30 tools, and the whole package itself might be 2 megabytes, hopefully, or 3 megabytes, and that's it. And they'll be like the top tools, and they'll solve a lot of issues. That's going to be super useful, not just for these resource-constrained environments, but also because I talk to the distros from time to time, and I say, you should make BPF trace by default. You should make BCC tools by default. And so when I talk to distros, such as Canonical and others, one of the big limiting factors is to make BCC a default install in Ubuntu means you need LLVM as a default install, the libraries as a default install in Ubuntu, and they can be large, they can be 20 megabytes or more. And so BTF and core, I see as a path to having some baked tools in all the distros by default. So BPF observability out of the box for everyone, and the same for BPF trace. Also going to be hugely impactful for the startups, because you have the same issue when you're a startup and you're building agents and you're telling customers, I want you to install BCC because I've written my agents in BCC, and now you have to install this other stuff. And so I see startup agents, it's going to be less than a megabyte of stuff, and it's going to make things much more practical. And so it's really going to help the widespread adoption of BPF observability.
Excellent. Thank you for your insights, and thank you for the presentation again. There have been a bunch of other really great questions in the Slack thread, so feel free to jump in right after that or after this and answer those questions there. Thank you all, and I'd like to turn it back over to Liz.
Thank you, Duffy, and also thank you, Brendan, for joining us from Australia at what must have been the middle of the night. So we really are all around the planet today. So our next keynote speaker, I am delighted to introduce, will be speaking about eBPF and microservices observability. Please give a welcome in Slack to Jana Dogan from AWS.
Hello everyone, today I'll talk about how we are using and planning to extend our use of eBPF specifically for microservices observability. So what makes me talk about eBPF and what actually qualifies me? A couple of things. I'm not a Linux developer. I'm working on monitoring observability and performance broadly. Multi-tenant platforms and microservices are my focus area. eBPF gives us new capabilities to do things we haven't done before, and this talk is going to mention how we think about it in the microservices observability context and what's the potential here. I came here to talk about microservices, but let me begin here with Linux. eBPF is a kernel extension, and traditionally speaking, Linux has a large variety of diagnostics and performance tools. I'm not sure if you've seen this great collective from Brandon Gregg, but it goes through various layers and the availability of the tools and gives us an image of what to use to troubleshoot each layer. Linux had this, it still has this rich ecosystem. It's great, but there are two main difficulties with it. As you look into this, you see that an application relies on so many layers, but the diagnostics data coming from these layers don't necessarily have that granularity. So it's hard to be able to, always see, hey, what's the impact of my app or my request on these kernel-wide subsystems? The second thing is there are so many layers, different tools, and different APIs to gather this type of, diagnostics data. It requires a lot of work to engage with these tools, and it's not really easy to extend, the data coming from Linux itself. Well, this is how eBPF was born. It's a programmable and an extendable way to diagnose Linux by writing small programs to intercept things and collect events. So what does eBPF do? eBPF is a very flexible mechanism that allows you to hook into user and kernel space to collect events of your interest. By using eBPF, you can hand off a program written in C from the user space and attach it to certain places. In this case, in this example, I'm going to diagnose networking events. eBPF programs can mutate data structures called BPF maps and allow user space programs to read that collected data. And then, you can take the data out and process and export it as metrics, logs, events, or traces. eBPF can hook into quite a large number of interesting things. You can hook it into function calls, and this is common for profiling and runtime execution tracing. You can hook into, similarly, into system calls. It can collect networking events, so you can report all the networking going on in a box. And the other thing is you can attach eBPF programs into kernel trace points. But let's take a step back. Let's talk about how does these new capabilities help us in the context of microservices. Before moving on to that, let me cover some of the big challenges about microservices observability. These challenges differentiate microservices observability from traditional Linux troubleshooting and may give you an idea of where traditional Linux tools didn't quite work well, but eBPF could be a better tool to work with. So the first one, in a microservices world, we don't only monitor VMs or processes. We care about the availability of these services and the user's critical path as a whole. When a request comes in and goes through various services all the way down to the storage, I don't primarily care which VMs are serving this request and the underlying availability of the VMs or the processes. I only start to think about them when there's an outage and an efficiency issue. And when things go down, I want to understand what service or services caused the outage. Then I want to know what I know about these services and their underlying resources to either mitigate or resolve the issue. I have to begin with identifying the particular service or RPC that has failed. And then I can begin to wonder actually about the underlying tasks, VMs, processes, and etc. I have to have a broader picture before starting to question the things that are Linux components. This is why new technologies like distributed tracing became popular in the last decade. It's not enough to monitor just the VMs or individual services. It's critical to be able to see things end to end. The second issue is the lack of context. When you think about our execution and scheduling models, we share the same box, the same virtual machine across various workloads. Linux kernel and its underlying components don't always have enough context to be able to enrich the diagnostics data. Linux knows a lot about the current networking going on in a VM and can generate out-of-the-box telemetry data, but it doesn't know how to decorate the data to make it more useful. Think about having a VM with many running processes. This looks like a typical MN problem, right? First, the diagnostics data coming from Linux should be labeled in a way so we can see what's the impact of a particular process. But in a microservices world, it's more complicated than that. We primarily like to see the world from the perspective of RPCs. We care about what's impacting us during the execution of a particular RPC. This is complicating the MN problem quite significantly because we have multiple, tens of thousands of RPCs handled by the same process. Then, in a containerized world, we isolate our workloads with containers, but beyond this, we logically group them as Kubernetes pods running in a namespace or an ECS task in a logical ECS service. These are logical groupings or namings, but it's important to collect them as context as we are collecting diagnostics data because it's how we navigate when we are looking at our dashboards. When we see a service being down, we want to be able to understand which cluster, which namespace, which pod. Context matters here. The other significant difference is we don't debug functions or syscalls like in the day of monoliths. Everything is an RPC or a REST request. We need to view diagnostics data from the perspective of RPCs for that reason. Even if we found out that there is a bug or a performance issue, we begin debugging at the RPC level. Once we find out that RPC handler is the origin, then we go and dig and find out, what might be going wrong in the lifetime of that RPC. Then we look into, the execution call trees, to dig further. This is where, our traditional debuggers or tracers are finally becoming more useful. The other big problem we have is the fact that there's so much data. And beyond the volume of the data, the vast majority of the diagnostics data is very repetitive. Think about the same RPC handler being invoked millions of times. When troubleshooting, we are really interested in interesting cases such as 99 percentile, right? Like in latency, for example. But events, logs, traces we collect will be very similar apart from these edge cases. We aggressively aggregate some data to become metrics such as latency metrics, but it's not true for every signal type. That's why it's critical to be able to have an extensible model where we go and increase the level of data collection in runtime dynamically. This gives us an option to figure out where the issue might be originated at and go and safely extend the collection to capture more logs, traces, profiles, whatever you name to diagnose. So in microservices observability, we want an extensible model. And the big elephant in the room, I've been keeping this slide to myself, but given the vast number of different platforms, libraries, environments, instrumentation is at least a 2-year roadmap for any organization. If you survey the compute platforms, cloud or not, the out-of-the-box instrumentation is pretty limited. The same applies to frameworks and libraries and other, third-party stuff. Not just getting all of the data is tough, but also making the data consistent is a tough job. Instrumentation has been growing, organically with manual efforts. So there's so much fragmentation in data types, propagation, and data formats, and as a result, we face a very pretty inconsistent, world. Sometimes being able to have a global view of all of your observable data is tough because it comes in so many different shapes and formats, and you might not be even able to ingest it all to the same system. Let me recap what I've been talking about the challenges in microservices observability. Networking is the core, out-of-the-box instrumentation is essential, extensibility in runtime is critical, and being able to amplify and enrich data in user space with custom programs is required. These all align nicely with the capabilities of eBPF. And it's not surprising that we are trying to utilize these capabilities in the context of microservices. So how does exactly eBPF help? It's quite useful in a couple of different areas. eBPF events coming from networking layers can be converted into out-of-the-box telemetry for networking. TCP, UDP, HTTP, gRPC metrics, or events are possible to collect without any code changes. You can also inspect text and binary protocols, such as database requests and responses. By relying on out-of-the-box network telemetry, it's possible to generate service maps without any code changes. This is an example from Cilium in Hubble. It automatically collects and visualizes the service map in a Kubernetes cluster. A little bit of an unknown, but eBPF can also help distributed traces if you consistently propagate the trace headers. Data collected with eBPF can be used to generate distributed tracing spans if there's a trace context in the header. In this model, you can generate the header at load balancers or sidecar proxies. Then you can only focus on propagating it while span data is collected without any code changes or anything. eBPF is also used to collect profiles continuously. It can collect both user and kernel space profiles. Here you see Pixie is collecting the profiles and adding some context such as Kubernetes pod name, the container name, PID, and such. So you can continuously profile without having to change any code. eBPF allows us to decorate data with context. For example, once you collect network events, we can ask a service discovery mechanism, or in this case, the Kubernetes API server, to resolve the source and destination IPs. And we can, resolve metadata associated with them to decorate the data we collected. And eBPF allows us to enable and disable collection in runtime. You can JIT compile new programs and attach new probes dynamically in the runtime. This allows us to momentarily enable and disable collection. There's been several community and industry tools that are already building on top of what I've been describing. Cilium and Hubble are, doing a lot of network diagnostics, service maps. They add context to the data. Pixie does similar things, and profiling. FlowMill is very focused on network diagnostics and low overhead. Not just the technology is there, we already have tools filling these gaps. So what's next? Is this a done deal? Not everyone is comfortable with writing C props, so a high-level language would fasten the adoption, maybe. Making the eBPF agents installed and available on our de facto platforms might be useful, especially if you want to provide a high-level control plane out of the box. Imagine you are provisioning an ECS or EKS cluster, and we give you an eBPF control plane to tweak the collection and configure where to export the data to. More platforms supporting eBPF would be great. At this point, not even every Linux platform is supporting it due to privileges and the security models. I'm thinking about, managed environments like Fargate supporting eBPF out of the box. We invest a lot in handling and processing the raw eBPF events. Every tool is currently implementing their own processing pipeline. There's a lot going on in the community, but it could be great to make some of these tools more reusable, so we can easily grab, mix and match what makes sense in terms of filtering, processing, and aggregations, and build our own pipelines. I think eBPF has a lot of potential to fill these gaps. It has potential to be the canonical starting point to collect observability data in distributed systems. We are interested in making it more available, utilizing it better for networking, and building high-level components to make our engagement easier with eBPF. That's all from me now. Thanks so much for listening. If you have any questions or feedback, please feel free to reach out live or via email. Thanks again so much.
That was great, Jana. Thank you so much. And we've got a ton of questions that came in. One that I just saw, a really quick one I want to start with is, can you use eBPF with Fargate?
Oh, you're starting with the hardest one. Actually, we've been working on this for a while because of, the security model Fargate, uses. It's kind of like, it hasn't been enabled for, user workloads. But we've been trying to, get it done later, this year. It's hard to, talk about in timelines, but we've been working on the Fargate support.
Very interesting. All right. So some other questions that came in. One was about aggregation due to high volume. Can you suggest a heuristic to automatically increase granularity during an outage?
Yeah, this is kind of actually a broader question. It's just not like eBPF. In metric collection, for example, it's very common to increase the whatever you want to capture in order to diagnose incidents. But it comes with a cost. It's not easy to increase the coverage of your collection in production, because it may turn into a more bigger catastrophic issue. So one of the things that we do, or previously I've done, was treating this as kind of like a canary. If you want to capture more data, you first apply that rules to a canary group and see what's going on. That gives you some signals that if things are going to be working out or not. You can roll it back, or just let them crash and try to reprovision things. But you try to use this canary approach, increase a little bit of data at a canary set, and then try to apply that rule to the other nodes.
All right. Another question that we had in from Zafir: is it possible that we could deploy eBPF on a host and we'd be able to view or trace functions that are happening in a virtual machine or a container?
I think this question is more of what are the function calls started at an RPC or an HTTP request or something like that. You may be able to have the exact execution tree captured, but a couple of things that we've been using in the past and currently is actually being able to utilize correlations better. One of the things that you can do when you're capturing execution traces, you can annotate them with arbitrary key values, and one of them could be hey, this was for this particular RPC, or this is for this particular HTTP request. When I was working on the Go programming language, it's very something similar actually. It's not an eBPF solution, but it's very similar. Go runtime is its execution tracer, and you can annotate it with the distributed tracing context, so you can actually see what's going on in the lifetime of a request. So it's more of just adding those type of metadata, annotating things, and trying to correlate.
All right, we're going to squeeze in one last question before we go to a break. So Sung Yu-wei saying that he's having problems with noisy nodes running 20% CPU all the time. Can eBPF help to reduce the, amount of noise from those RPC calls?
Yeah, I assume that this is about the RPC, specific RPC call is causing some burning some CPU, or doing something extensive that could be captured by profiling. And you can use eBPF to capture profiles continuously. We've been actually looking into this because capturing profiling continuously has been around for a long time, and we've been using our own profilers. But the idea of being able to just use eBPF, maybe utilize it for profiling. It's kind of like a compelling thing. So we can just use like one agent to, do more. So, we're looking into also utilizing eBPF to do better, continuous profiling.
Wonderful. Thank you so much, Jana, and thank you for being with us today and delivering your talk. So I think everyone really enjoyed it. There are lots of questions for you to answer.
Thank you.
So yeah, Jana will be in Slack answering more of your questions. So meanwhile, I think it's time that we have a quick break. We can grab a cup of tea or a cup of coffee or whatever is appropriate for the time of day where you are. We will be back at 10:20 Pacific time. We've got some great talks lined up all about eBPF for observability. See you soon.
Yep. Hey, break. And now hey everyone, welcome back from the break. And now we're going to transition into the observability section, in which we're going to run through a number of quick talks and really dig into some of the observability pieces. This first talk is going to be using eBPF as an SRE, a beginner's tale, presented by Sylvain from Reliably.
Hi everyone, my name is Sylvain Aguarch and I'm Reliably CTO. I'm here to talk about my beginner's journey into eBPF for SREs. Let's get started. So what are we talking about? Reliability. Industry defined that as a measure of continuity of service. SRE is a practitioner's approach to reliability, trying to surface to the stakeholders all those aspects of reliability, availability, all those system point of view to the stakeholders so that they are aware of it. Among other things, SRE codifies reliability goals, service level objectives, and their indicators, service level indicators. So for example, tolerating no more than 0.1% of HTTP failures over a given period of time for a given service. So where does eBPF fit into that? Well, because you can program the system and to raise some signals and some events, you can turn that into your kernel into a service level indicator generator machine. You just capture some, for example, HTTP transit, and you measure things like latencies or status codes and stuff like that. That's exactly what we're going to see in the next demo, which you can find on GitHub. All right, on the top left corner, I've got a simple web service that, web app that listens on port 8000 on localhost. I'm going to inject some traffic into that, and you'll see that sometimes some errors. That's on purpose for the demo so that we get to see something interesting. On the top right corner, I've got my eBPF program, which I'm attaching a socket to the service that is running on the left so that I'm getting a copy of all the requests that are passing by, and I can start measuring things like latencies or availability and of that traffic. Then I take that and I push that as indicators to Reliably, which allows me to capture the service level objectives that I am interested on. And that's exactly what we see at the bottom. So boom, that's what we have, a closed loop. We've closed the loop where we have eBPF now feeding service level indicators for me to see from service level objectives. And what we see here, for example, is sometime for that short period of time, neither the latency nor the availability are doing good, but sometime they come back. Obviously, that's a very short window, so that goes back and forth. All right, at that stage, we are now, we've seen a demo, but what is the key takeaways? What are the key takeaways for me as a beginner? Well, it was somewhat overwhelming because eBPF has a bit of a meandering learning curve. The documentation is a bit all over the place and the UX is raw, if not crude. But I think it makes complete sense. It's not a product, right? It's not governed by a body of people or business interests. It's a tech available to all through the Linux kernel, interface, and that's exactly fantastic. But that does mean that when you dive into it, you need to do a lot of work to really figure out what's going on. You don't really have an easy access to the tech stack from a UX perspective or documentation perspective. For example, what are the right practices? How many eBPF programs can I attach to a system before the performance crumble? What is the right level of hooks I should attach to? Those aren't really defined because, again, the tech is there, but it's up to you to define those. It's continuously evolving with the kernel, which is obviously a good thing because more points are added, but sometimes it means that the examples you find are not relevant or not working anymore. Or attaching a program at a function call may not work because you've released a new version and the function call has moved. Now, it's not eBPF's problem for that, but you have to be aware of a form of fragility into that. Distribution story is not there. The best you can hope for is a Git repository with some scripts that you can play. The BCC script, for example, repository has plenty of those, and that's fantastic, but that means really you have to just go and search for them. You can't just look for a package manager and say, download me this and install that. That doesn't happen yet. And a lot of access seems almost alien when you have had years for the last 10 years of containers, Kubernetes, serverless. All those abstractions have taken us away from the low-level code, so it's a bit daunting, but so much fun to actually go back to that and look back at where we started, what we learned probably at school or uni or in the early years of our experience. So it was a lot of fun, and I really suggest you have an experience like that. So key takeaways for an SRE, well, like we just said, it's nowhere there in terms of UX, of packaging and everything. So perhaps don't bet everything on eBPF yet, but do get started with it. Really, it's really powerful technology. As you saw during the demo, I didn't have to install any other company products, any other commercial product. I just add my Linux kernel, surfacing the event I needed, and I could see that as service level objective. So it has a lot of power, but it requires a lot of work to get there. So maybe you want to start with projects that are eBPF aware, such as Herbal, Falco, Apply, and start from there. All right, that was my journey into SRE, into eBPF as an SRE, and I hope you really enjoyed it. Have a fantastic summit, everyone. Keep rocking and keep coding.
Thank you very much for that talk. Remember to ask your questions in Slack. For this series of lightning talks, all of your questions should be answerable within Slack. We don't have time for a Q&A behind every one of them. So thank you again to Sylvain. And now I get to introduce Andrew Lang from Cruise, talking about observing GPU runtime behavior inside a self-driving car.
Hi, my name is Andrew, and I work on performance observability infrastructure at Cruise inside our self-driving cars. At Cruise, our mission is to transform the future of transportation with our all-electric self-driving vehicles. Today, I'd like to share how we found success leveraging eBPF and helping us develop a granular understanding of the behavior of our GPU applications at runtime. Solving this problem with traditional approaches can be challenging, especially so in safety-critical production systems. Most third-party tools for GPU profiling and tracing are not designed to be run alongside a complex AV stack running in real time with strict performance budgets. High performance overheads and lack of stability guarantees in these types of solutions often completely discount them from consideration for use inside our vehicles. What's more, these tools are often not configurable enough to enable highly custom instrumentation or custom software integration. Finally, another challenge is that these tools often only capture GPU-related activities. To paint a full picture of performance and system behavior, we'd want to also be able to capture non-GPU performance events and correlate everything in a unified way. When considering the characteristics of a BPF-based solution instead, we can see that this technology addresses all of these shortcomings mentioned for traditional GPU profilers. With all that in mind, let's now take a look at a solution which leverages BPF. Consider an application which uses CUDA for GPU programming. By attaching BPF uprobes onto CUDA APIs like CUDA malloc and CUDA memcopy, we can capture information about GPU memory allocations and data transfers, respectively. BPF enables us to get contextual information about these events when they occur. By capturing process ID and name, thread ID, and a stack trace, we can attribute these events to specific components in our stack, as well as specific code paths. Furthermore, by examining the contents of registers when these uprobes are hit, we can grab the allocation size or transfer size used. With all this data, we can generate powerful visualizations that can point us to potential areas of optimization in our code. With flame graphs, we can identify which components or code paths in our stack are allocating the most GPU memory, or for example, which ones are spending the most time allocating memory. With heat maps, we can identify bad GPU memory allocation patterns, for example, frequent and small allocations, which could contribute to memory fragmentation, or recurring dynamic allocations after stack initialization, which are expensive and necessary to avoid due to real-time requirements in our stack. By leveraging temporal data we get from BPF, we can also generate timeline views. Feeding data we capture from CUDA memcopy into these visualizations can give us an idea about PCIe bus contention in heterogeneous compute environments. Let's take a look at some slightly more advanced use cases as well. By using the CUDA host alloc API to allocate pen memory on the host rather than pageable memory, we can avoid one extra hop when subsequently transferring this data to the GPU over the PCIe bus. By attaching a BPF uprobe onto CUDA host alloc, we can capture and store pinned memory addresses for later comparison when performing data transfers to the GPU. Thus, we are able to identify which, if any, data transfers were made suboptimally. Another feature of CUDA is the unified memory system, which enables for greater memory flexibility in CUDA applications. With this flexibility, however, comes a trade-off which results in poorer performance guarantees. And while there are solutions where unified memory is advantageous to use, we don't want to use this in the vehicle due to real-time performance constraints. To guarantee this, we can attach a simple no-op uprobe onto the CUDA-malloc managed API to catch any usage of the system at runtime. In CUDA programming, another bad practice is to queue work onto the default CUDA stream, which is inherently synchronous with all other CUDA streams. Once again, we're able to leverage BPF uprobes to catch behaviors that are not suitable for real-time execution in our AVs. We can see in these examples that with BPF, we're able to build systems that give us stronger guarantees about the runtime behavior of our GPU workloads in the car. This has immensely positive implications not only on the performance attributes of our AV software stack, but on the safety of our vehicles as well. If you're interested in working on performance problems in self-driving cars, please send me an email and check out getcruise.com. Thank you.
Thank you so much, Andrew. That was a fascinating talk. If you have questions for Andrew, remember to just throw them into the Slack and we can get those answered for you. Our next talk is Continuous Profiling in Production with eBPF, presented by Pete Stevenson and Omid Azizi from Pixie.
Hello, everyone, and thank you for joining us. Today, we'd like to talk about continuous profiling in production with eBPF. Before getting started, we'd like to acknowledge how much we've been able to lean on other open source contributions. Our short list of highly impactful underlying projects includes eBPF, BCC, and FlameGraphs. So today, we'd like to first get you into our headspace and talk about what the problem, what we were trying to solve and what the problem was, and then get into the technical details about the underlying architecture of how we solve it, briefly show you a demo of this in practice and action, and then we will surface a few of the technical challenges that we overcame along the way. So this story begins when we needed to profile our own application. We were actually using the profiler included with BCC. It's an eBPF-based profiler. It gave us great power in that we did not need to recompile our application or redeploy our application, but there was still a high amount of friction between maybe wanting a stack trace and the jumping through the necessary hoops to go and look at it. You would have to log on to a node in the cluster, turn the profiler on and off, get the data down, render it as a flame graph. So our vision here, after experiencing this, our vision was to have an instantly available profiler that was, at the bottom line, no hassle. And this is now built into Pixie, which as an architecture, you have installed on the nodes in your production cluster, what we call a Pixie Edge module, or PIM. And the PIM is fundamentally a set of eBPF probes that collect data, maybe data about HTTP request latencies are relevant to our topic today. The BPF probe would collect stack traces, and these stack traces and data sit in the PIM. But if the Pixie cloud, which is a perhaps on a separate cluster or your same cluster, needs to run a query, it gets the data off the PIM, aggregates it, and renders it in some certain way that is going to show in your web browser. So in our case, your web browser would initiate this whole thing, and the Pixie cloud would get data from the PIMs, and you would just see a flame graph of everything across your entire cluster. So right now, let's quickly take a look at that in action. What I show you right now is my Chrome web browser communicating with a self-hosted open source Pixie cloud, which is running on a fresh Google Kubernetes engine instance. And then there's some more stuff on the cluster. For example, this online boutique toy application. And maybe we're interested in debugging the server front end portion of this, and we can look at these stack traces, zoom in a little bit, and maybe we notice there's a syscall here taking up some CPU time, and that might just be surprising, might be a clue about what you need to optimize. So in the interest of time, let's get back to our technical challenges and describe a little bit about what we found. And at the outset, we knew that the BPF piece of this, the probe itself, was very efficient. The cost of just getting one stack trace sample is about 3,500 CPU instructions. And you don't need to sample these at a very high rate. We chose 91 Hertz or every 11 milliseconds. And when you put that together, that should be less than 0.1% CPU overhead. But as we built this, what we found is there are other overheads that can cost you. And some of these are BPF or BCC related. And we would just like to refer you to our blog post where we describe how we reduce these other related overheads by about 4x. And in summary, we'd like to once again say we are now an open source CNCF sandbox project. Please check us out. You can clone the repo from GitHub. You can get your eyeballs on it and send us feedback or suggestions. And in fact, we would welcome some contributions or any directions or new directions and ideas. And with that, we'd like to say thank you. Thank you for listening.
Thank you, Pete and Omid. Reminder again, throw your questions in there. Saw a great Slack message from Carlos Santana talking about, I heard an SRE say that writing an eBPF program sits between YAML and Bash in terms of complexity, which is a pretty funny statement. The next talk we have up is container level network observability with eBPF, and that will be delivered by Ian Pye of Kentic.
Hello, I'm Ian Pye, and welcome to my kitchen. Also, welcome to our talk. This is container level network observability with eBPF. I'm presenting joint work with Will Glauser, and we're both at Kentic. Let's jump right in. So, container networking, why should I care? Well, you have a container, you have an application running in a bunch of containers, and people are telling you it's not working. Is it that network? Is it the application? How can you quickly identify what the problem is? If you inspect the state counters, look at TCP problems, you can see are the bytes going as they should? And if they are, you can dig in. And if they're not, you can look at the application. Another common use case is top talkers. Network is a finite resource. You have 1,000 containers, and you want to quickly identify which one of these 1,000 containers is taking up all of the bandwidth and sending all the packets. Lastly, we have a security use case. You have 1,000 containers, and they're all talking to various endpoints. You want to have a whitelist and a blacklist, and really observe exactly who everyone's talking to, sort of a firewall case. So why is this hard? Well, so let's take a look at a typical Docker setup. This is an image I found online, and it sort of illustrates the problem. So what we have here is two containers. They want to talk to each other. They want to talk to applications running on the host OS, and they want to talk to applications in the external network. By my count, we have 4 interfaces, and in a traditional world, you'd want to monitor all 4. This is really the point of this talk, is that when it comes to network monitoring, you don't want to think about the network, you want to think about the kernel. Monitor kernel state, let the kernel tell you about the network. And jumping right in, what are some alternatives? Well, we have PCAP. PCAP would give you the data you need with the expense of high CPU and having to send every packet out of kernel space into user space and just look at the headers and toss it all out. You still have the dynamic interface problem where it's working on a per interface level, not on the kernel level. Service mesh would get you what you need, but it would be extremely complex to set up. And you also have the problem of moving local traffic into non-local network all of a sudden. And lastly, we have eBPF. The kernel knows all about the bytes and packets coming in. We can just ask it to report things periodically. So how does this all work? As a demonstration here, we have an open source tool called Convis, Container Visualization. This is available on GitHub at kentic/convis. And here's a quick example output. Takes no flags, takes no arguments. You simply run it as root, and it starts spitting out exactly what TCP connections are going on. I have a simple container, which is running wget, and you can see it's recording the connection and the close events here. Also, we have Chrome snuck in a close event as well. And so you can see how it's really recording everything on the host, not just a specific interface or container. How does it work? So take a look at bytecode.c, and you can see that we're instrumenting 4 calls really. So these are basically around setting up a TCP connection, accepting a TCP handshake, and running a TCP close. Diving in further, we have, if you look at it, the magic here is really happening on line 157. So when you instrument TCP close, you get a struct sock, and that contains that's basically a pointer right to everything that the kernel knows about that connection. And then we simply turn it into one of our custom events. We have source address, dest address, sort support, dest port, remember N to H, that's network byte order. And we just sort of sticking in our custom event ID, and protocol is 6 because it's always going to be TCP. Lastly, we simply tell it to go right back out to our recorder with our event output. Jumping back up a little bit, let's look at the Rust level. Rust has made a lot of strides here lately. There's a IA crate and also a Docker crate that we're really leveraging very highly. This is the main event loop right here. And what we're basically doing is we simply load up the code, make sure it looks good. We load up a Docker crate to tell us about all the containers on the system. And then at line 42, we call code.exec. We simply wait for events to come back and print them out. Code.exec is leveraging the IA again. We simply connect the probes and send them in with really just very straightforward kprobe.attach. And then here's the where we receive the events from the kernel, and then we pass them back to that main loop again. Once again, it's Ian Pye, and I've been presenting work with Will Glauser, and this is all available at github.com/kenticconvis. Thank you for your time.
Thank you, thank you. Convis looks really fascinating. I might play with that one after. So now we're going to go to a short break. I think it's going to be about 5 minutes, and then we're going to come back to one of my favorite events of the day, the first live work through of the first Capture the Flag event. If you haven't checked it out, maybe you could use these 5 minutes to review it. It'll be on the eBPF Summit page. All right, welcome from the back. I hope you got some exercise during this short break. Get up and stretch your limbs and such. Now we're going to jump into a live solve of the first challenge, and welcome Tabby.
Hello, welcome back, eBPF Summit. Thank you so much for coming here to be with us and to try to hack our way out of this container onto the network with us. I'm Tabitha Sable. I'm a Kubernetes maintainer. I work to help advance security strategy at Datadog, and I've been an avid CTF participant, team member, and organizer for some time. This challenge is a ton of fun. We have to advance the plot here in the CTF, we need to be able to talk to a server out over a UDP connection, but unfortunately for us, that has been blocked by our enemies. And so we're hoping that using BPF, we can bypass this problem, get a code that we need in order to help and be able to bypass the blockade in the story here and go get our friendly bees. So we have 4 awesome hackers here today who are going to try to do this for us, and they will introduce themselves.
Hey, I'm Martinas, joining from Swiss village in Swiss Alps, and my favorite dish is pineapple pizza with ketchup.
Hi, I'm Cornelius, I'm from Zurich.
Hey everyone, I'm Louis. I'm joining you from New York.
Hi everyone, I'm Paul. I'm joining from my little sister's bedroom in Brittany, in France. My preferred dish is probably ice cream.
All right, so Paul, it looks like you have got the CTF challenge environment up and running here, and now you got to figure out what's the situation and what do you want to try to do with it. So let's go, and we're all here to help.
Great, let's get started. So basically, I started the Fedora VM. So if you follow the instructions, you can do this at home and you can reproduce everything we're going to do today. So I started the VM, then logged into it, started the Docker image, and then I have this small message. And so basically the goal here, as Tabitha said, is to connect to this IP and this port over UDP to probably get some answer, I'm guessing. Okay, so let's try to do this. Maybe that's the first thing we can do. So in the instructions, we have a command ready to just connect to this. So I'm going to try that. Obviously, I'm not getting any answer if I try this. So what can I do next?
Maybe let's check with TCP dump what's happening.
With TCP dump, okay.
I'm pretty sure I've never had a network problem that I didn't try to apply TCP dump.
And that's true. Okay, so TCP dump, let's see if I have it at least. Yeah, okay. TCP dump, maybe.
Do we know the device?
Yeah, you might want to do.
You want to do the routing table, maybe? Or
let's do everything.
That works.
Okay.
Yeah, let's do it.
Yep, catch all.
Okay, so UDP and the host I'm trying to reach. That looks all right. And let's try this again. And we don't have anything. Okay, so it looks like nothing is egressing on the device, I guess. But one thing that was catching my attention is in this message, there's something about IP tables, maybe. And as Tabitha said, it is actually an IP table rule that should be blocking this signal. So let's try to see this maybe. So this is the command from here.
Could you pass -C? This will print the counters for the rules.
Good idea. Okay, so we have the counters here. So what we can see is one rule. It is dropping everything that is UDP and destined to this IP, which was the IP we were trying to connect to. And 3 packets have been dropped already, so I guess that might be my 3 packets, maybe.
Seems likely.
You can try another one just to make sure.
Yeah, just to see it.
I'm personally a big fan of IP tables dash lowercase v lowercase n big letter L to kind of see this same thing, but I like the format of it.
Like this. Yeah.
Yeah, so you did hit it.
Okay. Yeah, so it incremented from 3 to 4. Okay, good.
So the firewall works.
Next.
That's a good sign.
It is a good sign.
I guess the rules are saying that we are not allowed to modify that rule.
I think if you try to modify that rule, the results might be funny.
Yeah, the container might be killed, actually. Don't do that.
Oh, yeah. Okay, maybe let's not do that. Okay,
but try it at home. It's actually pretty funny.
Yeah.
But I think the message says something else, right, about the BPF folder. And since this is the BPF summit, it might be relevant too.
Yeah, it's not a net filter summit.
So it says I have left you a sketch in the blueprint folder. So the blueprint folder. Okay, that's pretty good. So this is the one, and I guess we have some stuff in here.
Oh, there's a README. Huh.
This is so nice. Okay.
As much as I love make, like, what is this make file actually doing?
Let's look. Okay, so it's building BPF, like some BPF program with Clang, I guess, here, compiling it. And then here we have some TC commands, which I'm guessing are maybe to load the BPF program in the kernel.
And it's acting on that WG0.
Oh, yeah. Yeah.
Which is a ViderGuard device.
Mm-hmm.
Yeah, that one.
And there's a route to that?
Right. Yeah.
Cool. Cool.
So everything
Maybe let's open the program.
Yeah.
Are you Emacs or VI guy?
Can't start the flame wars on a company challenge.
Ed is the canonical editor, and that's all I have to say about that.
It's gonna get dirty.
Okay, so we have some BPF program. If you've written one before, it looks familiar. So there's one first BPF program here for egress. And it looks like, yeah, there's a second one here for ingress. Or at least it's called ingress. I don't know if that's a trick. Maybe. Oh, and the ingress one is complete according to the command. Like we don't need to change anything in there.
So from a high level view, like what we would like to do with this BPF program, I guess is one question.
Yeah, so I guess we need to bypass the IP table rule. So let me check the IP tables again.
So from the make file, I think we see that it's going to be attached to the TC ingress and egress. Mm-hmm. And this rule should be executed when? It should be before the TC egress, right?
Yeah.
So I guess we can do some modifications of the packet in that program.
Yeah, you mean like modify the packet so that it doesn't match the IP table rules?
Yeah.
Okay. So it's matching only on the IP and the protocol. I guess we're not going to modify the protocol, but that's
I don't think I want to write a state machine in BPF. Yeah. That sounds hard.
So we can modify the destination IP, I guess. But yeah, I guess if the ingress part is already complete, Yeah, so it looks like this is what it's doing here, right? So we have a BPF program on ingress. It's parsing the packet, so pulling everything from the packet, getting the pointers to the start of the packet, the end, checking if it's large enough. Okay, checking if it's UDP, checking if it's the IP address we expect for the source and destination. And then it's rewriting the source IP address. Oh yeah, the source IP address. Okay.
So it looks like it's doing a reverse DNAT, no?
Yeah, it looks kind of like a stateless DNAT. Yeah, reverse DNAT. So I guess we need to do the the other way around, so the DNAT in the egress one. Okay, so the idea is, if I understand this correctly, I'm not sure if that makes sense. We need to change the IP address, the destination IP address, so that it doesn't match the
IP table rules.
IP table rules.
Yep.
Okay.
And we also have a constraint on the DNAT on the ingress. So you'll want to use a particular IP address.
Oh, yeah.
I mean, or disregard the comment that says you don't need to edit anything here.
Yeah.
I mean, this is a CTF. You disregard whatever you want.
Yeah, but what do we do if we do that? Then
Well,
we
then
have
you
to
have
rewrite
to-
everything.
Yeah, you got to take more into your own hands.
So I guess we can just copy paste the code, no, and modify some
that's
bits.
what I was, because I'm not going to do the like checksum replace and everything by hand. I never did that before, so okay.
I think there's an option in SKB store bytes that's supposed to fix the checksum for you, but I wonder if that isn't working or something.
I don't know. I've never used that before. Okay, so let me try and maybe copy paste this. Okay. Okay.
And do we want to modify the source or the destination address in egress?
So if we just go by the what the ingress part looks like, I guess we want to modify the inverse of the ingress, but I'm not sure if that makes sense.
Yeah, I think it makes like we want to change the destination address.
Yeah.
Then we'll bypass the rule.
Yeah, makes sense. Okay, so let me rename this. Does this one needs renaming?
Yeah, so this BPF program is going to run when the echo command sends the UDP packet to the interface, right?
Yeah.
Gotcha.
And it's going to run after the IP tables rule. Is that what we said before?
Yes.
Yes.
Yeah.
Because it by the time TC gets to see the packets, they've already been queued to an interface.
Yeah. Yeah, makes sense. Okay, so basically we need to send the packet with an IP address that is allowed. And once it went through IP tables, we can modify the destination IP address to the actual IP address we want, right?
Yeah. Let's see how many copy paste errors you will make.
Yeah, this is tough with just like a stock Vim editor.
Yeah, people are watching you, Paul.
Thanks. You're supposed to help me. You're not supposed to.
Oh, come on, you got this. Check that.
I guess I need
check
to change
that you have
one.
your constants the way you want them to be, though.
Yeah.
It's okay. Just think backwards and in hexadecimal. 100, 202, 1.
So what's the IP address we want to? Oh yeah, it's the 1, right? If I remember correctly, the instructions.
Yeah, because that's the real server from the instructions.
Okay. So what's the corresponding IP address? I have it here.
So I think it's in the big endian notation in network endian. So
just the first byte.
yeah, I think you just had to change the most significant.
Oh yeah, yeah, makes sense.
Yeah.
So
cool.
like this.
Did you remember the CA64 part, or did you read it off of the screen? Okay, nice. I don't think I could have remembered that either.
No, I don't remember that either.
You don't speak hex?
Only binary.
How does this look? Do we think the C compiler is going to like this?
Yeah, we can try to compile and see.
Yeah.
I mean,
that's what the compiler is for, right? It's the tool that you put your code in and it tells you your syntax error.
Non-void function does not return.
Line 52.
That's only a warning. Warnings don't matter when you're in a CTF.
Ouch. Okay.
Actually, probably something bad would have happened if you didn't return there.
Okay, this looks good. Yeah. What? Oh yeah. Hack.
Too much TCP.
Yeah.
You got stuck.
Okay.
I think you can type make run, or what was the target? Yeah. Make run. It will attach the. Yeah, cool.
Okay, so we can maybe check if
Hey,
it's there.
dude.
What?
Oh no.
No.
I think.
Oh, put a big X on your TCP dump so that we can see the hexadecimal contents of the packets.
Oh.
Yeah. If you want to see the attachment, you can do it with TC. It's like TC filter dev.
So TCP -X?
Capital.
Capital.
Oh, okay. I've never used that before. Okay.
I think you need to change the destination IP address, no?
Oh, right. Yeah. Okay, so what was the IP address we used? Like
was 3.
Yeah.
Okay.
Oh,
that's too easy. I didn't even type anything.
Nice. Let's flip over. Let's look at the packet.
Very cool.
There it is. So look, by the
nice.
time you actually see it, we're really talking to 1.1 on the interface, but the kernel doesn't, like IP tables doesn't know we're doing that.
Yep.
Ha, so eBPF versus IP tables 1.0.
So like the thing that gets me about this is TC. You're classifying traffic for traffic control. Why is it that you can modify the contents of the packet in a BPF TC hook? And I think the answer is because it's eBPF. Like, it's programmable. How are they going to stop you? So like, I love this because you can do it, but it's like, oh no.
So I'm curious, to continue to block this problem, right? You would just have a wider IP table rule.
Or not allow untrustworthy individuals such as ourselves to run BPF programs.
Yes.
Yeah, probably. Yeah, I mean, you need to be privileged to like load the BPF program in this case. So yeah, if you're root on the machine anyway.
But it's pretty neat to see that we can actually modify the packet in there.
Yeah.
Thank you all so much, and congratulations for finishing this, like, even within 20 minutes. Like, that's pretty fabulous. We are now getting here to time. So as we get to the top of the minute, any last thoughts?
I think I really hate pineapple on pizza.
I'm going to
mean,
finish my pizza.
Honestly, I like pineapple on pizza too. So yeah, thank you so much. We will now turn it back over to Duffy to introduce our next group of speakers. Thanks so much for playing. Thanks so much for tuning in. The new challenge is going to go live soon. You'll see it on Slack, and we'll see you tomorrow at about this time to live solve that one.
That was amazing. Congratulations to our solving team and the wonderful Tabby Sable for not only solving the problem, but doing it bang on time so that we are right on schedule. So in case you didn't catch it, stage 2 of the Capture the Flag is now public. You'll find links to that in Slack. You'll find them on Twitter, and it's all posted on the website. So that's ready for you to go and solve. But don't rush off and do it straight away, because we've got some amazing talks for you to watch first. So this section is all about a subject very dear to my heart, this section on security. And our first talk is from my colleagues Natalia Ivanko and Jed Salazar. They're going to be talking about keeping your cluster safe from attacks with eBPF.
Welcome to the eBPF Summit. I'm Jed Salazar.
And I'm Natalia Ivanko.
And today we're going to be talking about how to keep your cluster safe from attackers with eBPF. Have some really cool stuff to show you. So really quick, I just wanted to kind of lay out like who this talk is really geared towards. So we're basically talking to the folks who are responsible for running and maintaining a Kubernetes production environment. So this has multiple names: DevOps, cluster admin, what have you. But we're kind of just targeting this talk to folks who are running a large production environment. We know that you're interested in automating your security because you're probably automating all the things. You likely have some interest in security. Maybe you're not a security expert, and that's kind of perfect. And of course, when you're asked about your favorite text editor, you're probably going to be suggesting Visual Studio Code. Of course, we know the type. So what are we going to be talking about today? Well, we're actually going to be talking a little bit about how we can use cloud native kind of principles to actually bring in security to your environment. And the thing to think about here is that cloud native security has a lot of potential built in. So unlike the days of running, just standard jobs on VMs, we're obviously using things in Kubernetes like pods, and there's some benefits there. Like, for example, we can really heavily sandbox pods. So sandboxing isn't really a new concept. It's been, in things like Chrome OS and iOS for a while. But we can utilize these sandboxing concepts to really kind of bring security into cloud native. So, I kind of list some things here like SecComp, AppArmor, domain aware layer 7 network policy. So basically what we can do is make sure that the pods that are actually running in the environment really only have access to the resources that we explicitly define. And we're kind of putting them in that sandbox. And this goes as far as, running things like Firecracker or gvisor. Microservices kind of get a bad rap for bringing in additional complexity, but there is potential there to bring in some simplicity from microservices. So for example, if you have, a minimal base image that you're using for your container, you're basically providing a minimal attack surface as well. So you have a minimal amount of binaries. And then, microservices kind of follow that Unix pattern of doing one thing and doing one thing well. In addition to that, if you think about it, a microservice, if the infrastructure is represented as code, or if the application is represented in code, it's actually codified, and you can be able to kind of reason as to what that code is doing. And then, of course, we wouldn't, be here without saying that the observability is top notch, right? So eBPF really provides an optimal environment for container security observability. And in addition to that, even some, capabilities to protect the system, as well as being able to observe some attacks. So with that said, I wanted to talk a little quickly about some observability best practices. So the first thing is that, once you basically turn on the observability faucet, things can quickly become overwhelming. So, you're just gonna basically, if you look at the observability, you're kind of looking at everything that's happening within that environment. If you have, a ton of microservices and you're scaling those microservices, you're essentially scaling what that observability looks like. So we really wanted to lay out some best practices here to kind of help you in this journey. The first thing that we'd recommend is as we're going over this stuff, try not to focus on individual system calls. If you've ever run strace on a machine, you know that system calls happen all the time. And there's a flood of data there. What we'd recommend from a security perspective is really to try and focus on the patterns of attacker behaviors. And this is, generally referred to as TTPs in the world of security, which is techniques, tactics, and procedures. But this really kind of lays out the patterns of attacker behavior. So for example, list some examples here. So one is persistence, how do we actually maintain a foothold on a system? Privilege escalation, how do we basically go from non-root to root? Or maybe from a container to a node? Lateral movement, once we've actually popped a pod, how do we actually kind of, move laterally throughout the environment? And what we're actually going to be covering today, and what Natalia is going to be showing us, is this really amazing demo to kind of break open that and take a look at some specific tactics, techniques, and procedures. So in this case, we're going to be looking at I'll list out a couple of examples here. In the case of persistence, you might have the root or maybe a standard user's authorized keys in SSH. Obviously, this kind of gives you the ability to actually have long-term persistence, and it might, kind of circumnavigate things like IAM, et cetera, depending on your cloud environment. Privilege escalation. So, in the Etsy Kubernetes directory, you might actually have the PKI or access to the manifest there that would allow you to basically, potentially escalate privilege or impersonate a specific Kubernetes system. And then lateral movement, right? So we might be able to look at things like, network flow logs to 169.254, which is generally referred to as the metadata server based on the cloud environment. So what we're going to be showing today is not just how to observe, but how to actually stop the badness from occurring. So basically what we've advocated for so far is asking the kernel to watch over the system with eBPF to be able to identify and witness, are we being attacked, and what does that data actually look like? But what if we could actually just ask the kernel to stop the attack instead of just, looking at it?
So from an environment perspective, let's assume that we have access to a GK cluster, and that's what we can see on the terminal. And on the same cluster, I actually have Cilium set up and running, which monitors all the Kubernetes workloads. And with the help of eBPF, it also provides security, observability, and also enforcement for them. So in this specific scenario, with the help of eBPF, we are going to monitor specific system calls to a particular file and terminate the process if that specific system call was actually invoked. In this specific case, we are going to monitor the syswrite syscalls to the SSH author key file and kill the process if that syscall was actually executed. So in this case, we are going to observe and monitor if someone externally would try to write into that file inside from a container, for example, insert there publicly, and we will try to kill that process and stop the badness. So now our main question will be, can we potentially create a backdoor to one of those nodes on the GK cluster? So as a first try, I try to spin up a pod with a privileged equal true flag. This should be enabled by default on Kubernetes, and this removes all the sandboxing mechanism inside of this pod. So we can actually see the pod spec here. And then we can actually check that it is up and running. So we can see that it was actually created and running. And note that the privilege equal true is an extremely powerful thing since we got all the permission that a root user would have on the node. So we can try to exec into this pod. And then we can actually check if we have resources on the host. We can check it by running cat proc partitions. And then we can see that the partitions that are listed here are actually partitions from the host. So now we can try actually mount one of the partitions inside to this container. Let's say this is SD1, and we will mount it under the TMP folder. So now we can actually inspect what is inside this mount. Maybe I can insert my public SSH key and get a backdoor. So let's just try to go into the SSH folder and then see what's there. We can actually find the authorized key file. I'm going to edit it with Vim. And then, well, the process was killed. So what's actually happened, the generated eBPF program, which was actually configured to monitor all the syswrite syscalls, which can happen to the authorized key file, actually terminated the process. So that's what we can see on the terminal. And then if I try to cat the authorized key file, we can see that actually nothing was inserted. So thank you for your time and your attention to watch this talk. We will hold a short Q&A on the Slack channel, and we will do a follow-up as well.
Thanks, everyone.
Thank you to Jed and Natalia. Don't forget, everyone, that all our speakers are on Slack. So if you have questions, you can find them, post your questions, and I'm sure they'll be happy to answer. So our next security-related talk is from Iago Lopez Galleras and Mauricio Vasquez Bernal from Microsoft, and they're talking about extending systemd security features with eBPF.
Hello everybody, we are Iago and Mauricio. Today we are going to show you how we use eBPF to extend the security features of systemd. Some months ago, systemd got support for eBPF. What it means for us is that now we are able to write eBPF programs that are used by systemd using pseudo-C, and we can use eBPF to load them. Before this support was introduced in systemd, those programs were writing using BPF assembly. This support is interesting for us because now this is much easier to implement new eBPF-based features in systemd, mainly because we don't have to worry about writing those programs in assembly. We all know that this could be very difficult in some cases. And the other advantage is that we have the full eBPF API available. So we can use this library to handle the maps, handle the programs, attach the programs, and so on. And the advanced features like compile once, run everywhere are also available for us. The first property that we implemented is called restrict network interfaces. By using this property, we are able to limit the set of network interfaces that a systemd service can access. This property supports the allow and the deny list approach, and this is implemented by attaching two different eBPF programs to the ingress and egress hooks of the cgroup system of the systemd service. For each systemd service, we have a hash map that contains the indexes of the network interfaces that are allow or deny. And this support is not already present on systemd, but we have a PR that has already got some review, and we are waiting for some extra review before merging that. I will show you a quick demonstration about this support. In this system, I have two different network interfaces. I have one interface that this is the loopback interface, and I have another interface that I use to reach the internet. By using this command, I tell to systemd that the processes that are executed in this service are only able to access this network interface. In this case, this is the interface that I use to reach the internet. This IP address is on the internet, so this ping should work fine. If I try to ping my local machine there, this is not going to work because those packets should be sent to the loopback interface, but this interface is not on the allow list. What I can do in this case is to add the local interface, the loopback interface, to the allow list, and in this case, the ping is going to work again.
So the second property that we've implemented is the restrict file systems property. This allows processes in a system service to have access or not to certain file systems. Allow and deny lists are supported, as with the previous feature, and it is implemented by attaching an eBPF program to the Linux security module hook of file open. So there's a single and global BPF program on the host, and then there's a global BPF map that stores a mapping between the cgroup ID, which is the way the kernel identifies cgroups and hence systemd services, and a set of file system magic numbers, which is how the kernel identifies file systems. The pull request got one looks good to me already, but it's not merged yet, but we hope that it will be merged soon. So I'm going to show a brief demo of this. So here we have a systemd service that does a very simple thing. It cats a file in the TMP file system called hello. And the interesting line here is restrict file system, which is our property. And this allows access to the file systems of Btrfs and TMPFS. The Btrfs bit is needed because the cat binary lives in a Btrfs file system. And the TMPFS is to access the hello file. So if we try to execute this and we check the journal, we can see that the cat program worked well and it printed hello world, which is the contents of the file. So now let's imagine that we try to do something nastier and we try to access the proc file system, especially the file kcore, which is a bit dangerous to have access to. So if we try this and we check the journal again, we see that the operation was not permitted because we only have access to the TMP file system. If you want to know more details about how this is implemented, you can check our blog here that's linked on the slide. And thank you very much. We hope you liked this presentation.
Thank you very much. So our next talk is by Shruti Chaturvedi. She's from Meet Clara, and she's talking about strengthening application and network layer security by integrating eBPF-based CNI in Kubernetes.
Hello and welcome. My name is Shruti Chaturvedi, and in this session, we are looking at how to strengthen application and network layer security using Cilium, which is a really cool open source tool and a faster way to implement least privilege security in a scalable Kubernetes environment. So Cilium isn't restricted to Kubernetes only, but in this session, we are going to be looking at Cilium with Kubernetes. So what does Cilium do? With a little play on the word acronym, Cilium provides security, observability, and networking for workloads running on Kubernetes by leveraging the power offered by BPF. So now we understand the acronym. So how does Cilium really leverage BPF? Whenever we install Cilium inside of a cluster, as we can see on the right, we get these Cilium agents running on each node in the cluster. And what the Cilium agent is going to do is inject BPF or custom BPF programs into the Linux kernel. And the cool thing about that is the BPF programs get JIT compiled, so the execution is really, really fast. Not only that, every time your cluster network definitions change, the BPF programs, they get compiled and re-executed live without the need to reboot your system. In terms of network security, Cilium is a custom CNI which leverages hash tables from eBPF, and it eliminates the need of using IP tables. Hash tables are much more scalable than IP tables are. Cilium also supports the standard layer 3, layer 4 network policy for ingress and egress. Additionally, Cilium also supports application layer security, which means security based on API, DNS, and protocol definitions. So we have resource-based identity inside the Cilium, and environments where IPs are constantly changing, pod or container-based identity is really helpful. There are quite a few advantages of using Cilium over the Kubernetes network policy. So Kubernetes network policy, the natively only offer layer 3, layer 4 network policies, and Cilium add to that by offering application layer policies as well. And the other advantage that I mentioned earlier was that Cilium CNI uses hash tables to do all of the security mappings, and which is more scalable and really, really fast. So it reduces latency. So lookup times for hash tables are almost constant, and we don't need to reboot our system every time a new mapping is added to our hash table. With that, let's move on to the demo. So what we have here is a single node Minikube cluster with Cilium already installed. And with that, we have the Cilium agent and the Cilium operator. So this is installed as a part of the install.yaml file. And what this file is going to do is configure our CNI and also install Cilium agent once per each node and all other configuration that's needed for the Cilium CNI. The other thing that we are seeing here are some custom pods which are deployed as part of the deploy API.yaml, which is a Cilium example file where we have two different organizations, an old reference taken from Star Wars, and the two organizations are the Empire and the Alliance organization. And what we want to do is protect our API called the Death Star API from unwanted access, specifically unwanted access from outside of the organization. So if we have a client which is trying to access this API outside of the Empire organization, we want to restrict and block complete access to our API to protect it, because that outside client might be an attacker. So without a network policy in place, when we try to send a GET request at this particular URL, what we get is a OK 200 response from the API. And when we try to send it from outside of this organization, so X-Wing is a client or possibly an attacker, which lies outside of the Empire organization, we get the same response. Now, looking at the response, it is basically telling us all of the resources and the methods which the API supports. Now, this is not necessarily something we want anyone inside or outside of the Empire organization to get their hands on. So we don't want to allow this particular method. And let's try and see what would happen if we are executing one of these supported methods by this API. So first, let's try and send this request from inside of our organization. So TIE Fighter client, which is inside of this organization, we are trying to send a post request requesting for a landing. So we get a 200 OK, the ship has landed. So that is amazing. We want our organization, within organization, someone to be able to land their ship at Death Star. But let's see what would happen when we try to execute the same command, someone trying to attack Death Star from outside of our organization or the Empire organization, sending that same request. We also get the ship landed 200 OK. Now, this is not something that we want, and we want to change that. How do we do that? We basically are going to apply a layer 7 HTTP-based Cilium network policy. So with that in place, what I'm going to do is simply apply this command. And now we will try and execute the GET request from the same organization. So it goes through. That is amazing. Now, what would happen if I'm trying to execute it from a different organization? So this is blocked. And this is exactly what we wanted, to really leverage that least privileged security and that fine access-based security. So this demo ends here, and so does the presentation. We are at the end of it, and thank you so much for watching. If this is something that is interesting to you, feel free to drop an email to me, and also do check out Cilium since they're really cool.
Thank you for that, Shruti, and great to see a demo as well. So next up, we have Eric Sage and Melissa Kilby from Apple, who are going to be talking about how Apple use Falco. So it's called Think eBPF for kernel security monitoring.
Hi, and welcome to Think eBPF for kernel security monitoring, Falco at Apple. My name is Eric Sage. I'm from the Linux kernel team, and I'll be joined by Melissa Kilby from the security engineering team, and we're going to discuss how we deployed Falco at Apple. Before we do that, however, I'd like to discuss why the Linux kernel team at Apple loves BPF. There are inherent risks with running kernel modules that run third-party code in the Linux kernel. Kernel modules have full access to all kernel data structures and kernel functions. BPF programs, on the other hand, are limited to the BPF virtual machine, BPF helper functions, and are verified by the in-kernel BPF verifier. This makes them easier to audit and greatly reduces the impact of bugs and vulnerabilities. We also love that BPF programs reduce our usage of heavy, out-of-tree kernel bypass frameworks, large modules, and modules that are running third-party code that we have to audit. And we also love that we can reduce these modules into small BPF programs that are dedicated to a certain type of processing, such as XP programs for packet processing, probes and trace points for event tracing, and socket filters for filtering network traffic. We also love BPF because we can view, analyze, and debug BPF programs using a common set of tools built on top of libbpf, a library that works on top of the BPF syscall. For example, BPF tool, which resides inside of the kernel source, allows us to view BPF maps, BPF programs, and the number of times a BPF program has been invoked, and the amount of memory that the BPF programs are using inside of the kernel. We also love compile once, run anywhere, which allows us to run a BPF program using BTF type information on top of several kernel versions, which is a great improvement over our current strategy of deploying kernel modules. The last but not least, we love that it's kernel native and that we do not have to rely on out-of-tree device drivers, modules, or on frameworks and processes that are not native to the kernel, and that we get the full support of the Linux kernel development community. Thank you. Now let's hear from Melissa.
Falco monitors how processes make requests to the kernel. Syscalls never lie and have the potential to capture a full picture of attacks. Falco's rule engine enables effective on-host data collection. Let's demo how Falco can identify entire classes of vulnerabilities and attacker behavior off the chain together to a nice kill chain. Our target is a web application that contains an arbitrary file read vulnerability. The curl command uploads the PHP payload using a local file include. The listener on the attacker machine catches the reverse shell after unleashing the attack over a second curl command. That causes the payload to execute. The payload effectively hooks bash standard in, standard out to the TCP socket. It turns out that the package manager RPM is terribly misconfigured. The current user account can run the RPM binary, literally anything as root. Next, let's zoom into Falco's BPF driver. Falco defines various BPFs, and for instance, sysaccess BPF traces system call exits. BPF tail calls are made to jump into another eBPF program. This is because Falco selects the correct filler for each event type based on a conditional block. Within each filler, the event is parsed and relevant data pushed onto the ring buffer up to user space for Falco rules evaluation. When it comes time to optimize your Falco deployment, we recommend measuring the average time spent in each BPF using the BPF tool. However, granularity at the BPF tail call level is not yet supported by BPF tool. Selectively activating and deactivating system calls can help inform you about the tags associated with your deployment. In the BPF tool output, only the main BPFs will have the stats info, and they appear in the order the sections are parsed. Finally, correlating CPU and BPF times indicates that as the load on servers increases, more CPU is utilized, for instance, to process more system calls faster. Low-level control of every aspect of your Falco deployment allows for thorough control of resource utilization implications and customizations. For example, each additional system call included in your Falco rules will have different performance impacts. In a similar way, verbose logging can cause excessive data generation. Finally, centralized data science approaches are needed on top of the Falco logs in order to derive high-value and actionable insights and detections. Thank you.
Thank you to Eric and Melissa. And now let's go over to hearing about stories from BPF security auditing at Google, which is delivered by Brendan Jackman.
Hi, my name is Brendan Jackman. I work for Google in security. Today I'm going to tell you a couple of stories and things that I've learned from working with BPF for security auditing. My group is called Detection and Response, so we basically keep an eye on Google's systems, try and detect when unusual things are happening from a security perspective, when we're under attack, and respond to that as soon as possible. I'm obviously concerned with the Linux part of that, and this is about just an overview of how that looks. We've got loads of Linux systems, all the way from servers that are running important services down to this laptop that I'm using right now. And they're all constantly piping telemetry, information that could be interesting from a security perspective into our software pipeline, which is doing some sort of clever stuff. And then from there to a whole lot of very clever humans who are the people that will respond to any incidents that are occurring. So I fit in about here. My team builds the agent that actually runs on those Linux systems, and it's sort of the first stage of that pipeline. Just to clear something important up, these machines, Google machines, are like Google's own machines. My work laptop, but not my personal laptop, and not your Chromebook, for example. Yeah, so the kind of traditional way I suppose you'd do this would be with audit and audit D, and indeed we use it, but on the whole, it's just not flexible enough for our needs, and it can also sometimes be a bit too slow. So we started with a kernel module, and that's what we had for a few years. It was really hard to maintain for all the reasons that out-of-tree kernel modules are hard to maintain. So we turned to BPF. And we would like to be extracting this information at sort of as high a semantic level as possible. Most of the places where you could attach BPF programs in those days were quite low level. So it was like trace points, function calls, system calls, I suppose. But what we decided to do was contribute the BPF LSM. So that lets you write LSMs in BPFs, LSMs in BPF. And LSMs basically give you an API inside the kernel that notifies you about events of interest to security, and it's at quite a high level. So instead of being like this system call was made, it will be something like this process accessed this file, or this process executed a sub-process, or something like that. Yeah, so it's really designed to let you say, no, that process can't execute a sub-process because of this policy. But we use it instead to just record that that happened, so for auditing. So the first story I want to tell you is about atomics. The case I was looking at that motivated this project really was the programs that we run when processes get executed. And obviously that's something that can happen at the same time on different CPUs at once. So in that context, how do you generate a globally unique integer in your BPF program? There have always been ways of doing this, but it's something that seemed too difficult at the time to me for something that's so useful, being able to generate unique values. Atomic operations seemed like the way to go. So I went to the BPF office hours and I threw some informal slides together and I said, hey, can we add atomics to BPF? I was quite timid. I said, let's add helpers, I think, if I remember rightly. And the maintainers were really positive and open-minded about this idea. And they actually said, no, let's go one step further. Let's do it properly and add atomic instructions. So let's actually modify the instruction set. So I went away and designed it. I don't have time to go into too much detail here. At first, I was going to add some new opcodes entirely. Yonghong from Facebook had a really smart idea that let us add a huge number of new instructions without breaking backwards compatibility and without using up new spaces in the opcode space. So that was cool. This is what it looks like. I'm afraid I've got to skip over this a little bit. But yeah, the moral of that story was really that this is a really open community, and within like a few months of going to that office hours just to explore the idea, not only was the code there in the kernel with help from other experts, but we were actually getting value from that internally at Google. So it was a really fast turnaround and a really good investment. And yeah, I wish I had done more of it in the year. Yeah, I want to share a couple of insights that I learned about ring buffers. Our project's really all about getting data from the kernel into user space, and there can be quite a lot of it. So yeah, I want to tell you about why we moved from the perf buffer to the BPF ring buffer. I think in the early days, the perf buffer was how you pass data through a ring buffer to user space from BPF. But Andrew designed and implemented the BPF ring buffer. And that was a big improvement for us for two reasons. Firstly, the perf buffer actually enforces that you have individual ring buffers for each CPU. So I guess that was a decision to avoid having to contend for the ring buffer pointers between the CPUs. But that actually is a really bad trade-off, or is for us at least, against memory usage. Because if you have to have a ring buffer per CPU, most of them are going to be empty most of the time, but they're still using up memory that you can't use for other things. So that was an inefficient use of memory. Or if we wanted to be more efficient with memory, we had to sacrifice on the depth of the ring buffers, which kind of sacrifices our ability to tolerate huge bursts of data at once. And then the other sort of more minor downside is that those events can get reordered as you reconstruct them from the various ring buffers, which is something you can overcome, but it really adds complexity that you'd like to avoid in your user space agent. So we now, with the BPF ring buffer, we're able to share that ring buffer between all the different CPUs. But the cool thing is that because it's a flexible system, even though it's lockless, there is some cache line contention, I suppose. And if you wanted to avoid that, you still could, because you could do something like have one ring buffer per last level cache per 4 CPUs or something. We haven't had to do that yet, but it's really great that we have that flexibility. Yeah, and this is just another trick that we do with ring buffers. I'll start with an example. One of the events that we like to report from the kernel is processes being executed, and we need to report all of their arguments and all of their environment variables. And that can be quite a lot of data. I think it's like 6 megabytes at the maximum or something. If it's a busy period, the ring buffer might be full, and when that happens, we're going to lose a whole chunk of data at once if those messages are really big. And there's quite a simple solution to that. We just break those messages up. So instead of saying, here's a message that tells you there was an execution, these were its arguments, and these were its environment variables, we say, there was an execution, that's the end of the message, and later, I promise to give you the environment variables and the arguments, and they'll be linked by a unique value, a unique identifier. And that's actually why I added atomics. As well as being reducing the amount of data that we lose when the ring buffer is full, or really important data, it actually lets us do some sort of asynchronous programming as well, because we can now say an event happened, I'm going to report that synchronously, but later on I'm going to come back and when I've gathered the extra data that I want, and I can add that data on retroactively. So yeah, another trick that we use with ring buffers is what we call chunking. So argument vectors are a good example of something that can be really big, but most of the time isn't. So it's got this really dynamic size. Unfortunately, the ring buffer, in order to work with the verifier, needs to know ahead of time how big the messages that you're going to allocate are. And if you don't, your program won't load. So the naive solution to that is just to allocate the maximum possible size that your message could be. But when that's 6 megabytes, that's not really tenable. Yeah, what we do is we just, instead of allocating one very large message or allocating a dynamically sized message, which is impossible most of the time, we allocate a dynamic number of fixed size messages. And by adjusting the size of those individual chunks, we can trade off CPU in terms of individual messages being sent against memory in terms of this padding. So if the chunks are smaller, you need less padding, but you use more CPU because it's more individual messages. So that's just another flexibility that's really useful when it comes to tuning our system. So yeah, a couple of things about the future. For the last year, we've been pretty quiet in the community because we've just been really heads down trying to get these systems deployed internally and delivering all the value that we promised. But some exciting things on the horizon are DNS auditing, and that's got some really interesting challenges Florent's working on. So hopefully I'll have something to share about that at some point. KP's been looking into doing the kind of enforcement side of things with KRSI, which is something that it was always designed for, but we've never really been using so far. And the other thing is, like I said, we like to operate at this high semantic level where we can, but we're really often forced to drop down much lower and use things like trace points. So we're going to have to start looking into how to improve that. And hopefully there'll be some cool kernel contributions along with that. So yeah, thanks very much for listening. I hope you enjoyed it, and I'm here for questions.
Great to hear about Google's work with the community there. So now we're going to turn to IoT. We have Jalal Harouni from Open Devices speaking about BPF for bridging cloud and IoT Linux security.
Hello, yeah. So in this presentation, we are going to see how to take advantage of the BPF features that are being actively used in cloud native ecosystem, and see how to use them in and possibly to use them in Linux IoT devices. So I'm Jalal Harouni. I work on cloud infrastructure and software deployment to IoT devices. I also help build secure Linux IoT operating systems and contribute to around the Linux ecosystem and security in general. I would like to thank eBPF Summit organizers for this opportunity. So in the beginning, we have our motivation. So we have smart devices everywhere that are running Linux, leading the market. And also we have a lot of container images deployment on Linux IoT devices because it's more easy to deploy. So before, let's talk about the security mechanisms in Linux. We have usually two ways: auditing, monitoring, then mitigation. From the auditing monitoring point of view, we have BPF-based parsing, the next generation of tools, especially in the cloud-native ecosystem. And for mitigations, we have built-in easy-to-deploy features like namespace, seccomp, etc. We have built-in how to deploy features like mandatory access control LSMs, which are not that friendly to dynamic environments like Kubernetes containers and also to Linux IoT devices. We have out-of-tree features, and also we have new built-in BPF LSM and non-block. So how BPF is being used for cloud security? We have container runtime security to protect containers, pods, and Kubernetes deployment like Falco. We have a lot of tools around the auditing, monitoring, tracing. Also, we have Cilium that does a lot of network security and observability. Even Cilium implements next generation of load balancing based on eBPF. Cilium also have even load balancing between Kubernetes services, so not only at the network end, but also between Kubernetes services, etc. So let's see what are the attack surface on IoT devices. Usually, attack surface is trying to modify the storage, mount a new file system, attach devices, execute memory elf binary, so receiving payload, then executed directly using memory FD system calls, accessing special kernel devices, hiding modules, loading modules, arbitrary network connections, etc. So mitigation. From mitigation point of view, we can block such attacks, but by taking advantage of the new work that has been merged, the KRSA in the network, which is in the kernel-based BPF-based LSM, which allow us to filter mounting new file systems, blocking blocking remote operation to change the mount flags, mounting new virtual file systems. Also, we can block memory elf binaries by using BPF LSM. We can also combine BPF cap probes and the LSM to do one shot of tracing and blocking, and then do the mitigation without having that time where we do auditing, then go change some options of log to block after the auditing. So to block attacks, we can do this in one shot. We can also have BPF LSM to block attaching devices, loading kernel modules, BPF programs, etc. So what are the advantages on devices? Why we should use BPF for security in Linux IoT devices? Because compared to some other security features, we can combine BPF auditing, tracing, and mitigations in one shot. Minimal performance impact. It avoids some Linux kernel system potholes that are related to modern workflow, how modern workflow works, by taking advantage of control groups, namespaces, containers, etc. We may have security mitigation without full-blown policy rules. Also, not that much LSM conflict, since LSM stacking took too long to be measured, and basically it missed a lot of innovation, Linux security innovation in this area. From cloud perspective, we can have observability platforms that detect suspicious activities when we gather all this data from the devices. Why BPF for Linux IoT now? Because there are more friendly features in BPF that are more friendly to embedded and Linux IoT devices, like BTF that encodes metadata directly and debug information. And also we have core compile once and run everywhere to have portable BPF programs. BPF log is an ongoing, so it's a new tool, ongoing to have some of the security features that we did see in this presentation for Linux IoT devices. And thank you.
Thank you, Jalal. And don't forget to post your questions in Slack. So we're up to the last of our talks in this security section. This is Yanis Yakumis from Selfie Networks talking about network tokens with eBPF.
Hi everyone, my name is Yanis. I'm a co-founder in a company called Selfie Networks, and today I want to talk to you about network tokens and how we leverage eBPF to build token-based functionality for Linux environments. So what is a token? It's essentially a streamlined mechanism to transfer metadata between endpoints or between an endpoint in the network in a secure and scalable way. You can think of these as JOT for the network, and they are tailored for use by infrastructure and network teams. Network tokens essentially include a set of arbitrary claims, which are then cryptographically encrypted or signed to provide properties around integrity, authenticity, and confidentiality. They expire, so they have a short lifetime, and they can be bounded to certain fields like the source IP address to account for replay and spoofing attacks. There are different use cases where we can use tokens. Just highlighting a few here, we can use them to secure existing metadata. For example, we can wrap the overlay ID of a virtualized workload with a token in order to provide integrity and authenticity guarantees. We can use tokens to extend an OpenTelemetry identifier to the network layer to have better visibility on the live overflow. We can use tokens to access policy-based forwarding and network SLAs, or we can use them to do directly access control based on metadata encoded within tokens. I'll use the last application to describe how we use eBPF to implement the application, but they all serve very common characteristics in terms of the overall architecture. So imagine that we have two hosts. Host 1 is a backend node running in production, and host 2 is a front-end node running in production again. And what we want to do is make sure that only backend nodes can access the front-end nodes on the right side. And so essentially, every token-based application has two basic packet operations. One is insert a token at the egress with the necessary metadata, and then inspect this token at ingress and verify that it's valid, match it against the policy, and take the desired action. Here, as you can see, we are inserting a token where we are defining the metadata associated with this node. There is an expiration time and a bound IP, and this is encrypted with a certain algorithmic key and sent out. And on the ingress, we are just decrypting the token with a predefined key, and then look at the metadata, and if the metadata match, we let the packet go to the application. How we use eBPF to implement insert and verify capabilities. Essentially, inserting a token is straightforward. We use a TC egress program. We store a pre-computed token into an eBPF map along with the policy, and based on that, we decide whether we should include a token to an outgoing flow, and if so, what token should that be. We also use the capabilities of eBPF to expand the buffer, adjust length, checksum, and so on and so forth. On the ingress side, we do something similar. So we have a TC ingress program, which we use to detect and verify the token. Again, we use maps to store the policy and the metadata to match against, and if the token is valid and the policy matches, we let traffic go through, otherwise we reject it. One note here is that part of verifying a token is implementing a crypto operation. Right now we don't do this with eBPF at the kernel, but we use an XDP socket to make the buffer available from user space, where we use publicly available JOT and binary token libraries to do the verification there, and then re-inject the packet into the kernel stack. What are the benefits that we get from eBPF? We can transparently inject and verify tokens in multiple layers. We can do all the plumbing, change length, change buffers, add extensions with no application changes and no kernel customizations. We can redirect to user space in a very flexible manner, so we can do this only for the packets that contain tokens. It would be much better if we could do this using the kernel script API. So if there is a wishlist here, better crypto support within eBPF would be one thing to add. Another big benefit is that we can use the same code for both host-based applications and network or gateway-based applications. That allows us to do things at a single code base. And lastly, we can sort of like expand the initial model of injecting metadata on the side by exposing a direct API for applications to insert their own tokens using custom socket options. That's all. If you have any questions, feel free to ask now or send me an email. And you can visit networktokens.org, where you can find the spec and relevant code. Thank you very much.
So that concludes our section on security. We're going to take a quick break now. We'll be back in a few minutes with some more amazing keynotes and some talks about deploying to Kubernetes. Now, take the time in the break to at least stand up, move around a bit, maybe grab a drink. And if you have time, go and fill in the feedback survey so that we know what you're enjoying and how we can make the summit even better in future. See you soon.
All right, welcome back from the break. That was a quick one. We are going to be jumping into deploying eBPF on Kubernetes, or just deploying eBPF. Our first, this section is going to hold 2 keynotes, and then we're going to move on to sessions. The first keynote is eBPF and Cilium at Sky with Sebastian Duff, Anthony Comtois, Joseph Samuel from Sky.
Hey everyone, welcome and thanks for joining our talk about eBPF and Cilium at Sky. For some context, Sky are a player in the OTT video streaming business. So there's 3 of us who are involved in this presentation today. I will introduce us and then get on with the content because 20 minutes goes by quickly. So first of all, I'm Sebastian Duff, or Seb. I'm responsible for the core engineering department, and we'll cover a bit more what that is in the introduction. The second person is Anthony Comtois, who is a principal engineer who is working on the Cilium adoption at Sky. Anthony has a very deep understanding in the space, so we'll be talking in some more detail about the work which he is doing. And the third person is Joseph Samuel from CECG. CECG are a consultancy who have played a huge role in our strategy and adoption of Cilium at Sky. Joseph has also helped prepare this presentation and is online now to also answer some questions. So this talk might be a bit different. Rather than going into the deep technicals of how we are leveraging eBPF, we'll be focusing on the delivery aspects and how we leverage technology to gain a high level of confidence, mitigating risk to the platform and to the business. In the first section of the presentation, I'll give a brief introduction to what we as core engineering do, and I will hand over to Anthony to first talk about why we chose Cilium and eBPF, and to talk about the pipelining as a form of risk mitigation. So core engineering is a department within Global Video Engineering and Apps, which is responsible for the backend services, client libraries, and a portion of the clients supporting video and playout for Sky's OTT propositions. Some of the most recognizable platforms and propositions which are part of Sky, that are Sky Go, Now, which is formerly Now TV, and Peacock. In core engineering, we build a multi-tenanted Kubernetes-based platform as a service offering, which hosts about 90% of the OTT application workload. The platform is built as a white label product so that it can be built once and deployed many times to support the different organizations. As the underlying platform as for high profile propositions, we have very large complex requirements, including being highly available, hybrid cloud, multi-region, and active-active, all of this at high scale and low latency. On the next slide, we have some interesting stats which give a brief view of the scale which we're working at. So the multi-tenanted platform currently supports 13 departments with over 90 teams, which is about 1,000 engineers using the platform. These teams are all using a wide variety of different technologies, so our goal is to provide a consistent interface for everyone, and we largely do this by leveraging Kubernetes and building custom tooling and libraries which teams can leverage. From the technical stats point of view, we have over 300 unique applications deployed to the platform with more than 60,000 replicas across all of the environments. And to support the required scale, we have performance tested our central services such as Ingress to 1 million TPS. And that's enough for me as an introduction. Over to you, Anthony, to talk about why we chose Cilium and eBPF.
Thanks. So why are we going to use, why have we been using Cilium? So we've got a few security requirements. So we want to restrict like the communication within the cluster. So from pod to pod communication, we make sure we can allow a specific tenant to talk to a specific databases or block them. And we want to make sure we can block some malicious IP defined by the security team, and making sure so the tenant cannot override the blocked IP at the cluster level. And we want to move towards a least privilege access model. So how we can do that? So you've got like the IP tables way where we know there is like some downside in terms of and scalability concern. There is a few talks on the web already talking about that, but now we're going to rely on eBPF and Cilium, and that's why we have been choosing eBPF to make sure we can scale for the current cluster figures and number. So we're going to rely on the eBPF programmability, where you can inject some eBPF program inside the kernel and interact with the network stack, and rely on eBPF map to share the data. Cilium agent is going to update the data, and is going to give us a more efficient load balancing and network policies propagation. I'm going to rely heavily on deny rules to block any malicious IP, for example, and host networking. And with the low overhead of eBPF, we have the nice observability tools like Hubble and Cilium Monitor. So when you decide to embrace new technologies, and at some point you have some live and existing cluster, and you want to make sure you're gonna mitigate the risk by adopting a new technology. So we are gonna rely heavily on testing to make sure we are not affecting any tenant and the platform overall. So you have a pipeline, you have a Git repository, you commit your change, and you're going to push. And as part of the build phases on the CI, we've got a CI agent which can run the test, and that's all the localized tests you can imagine, like linting, DDoS to just check the overall and inspect Docker images, and you can run some vulnerability scanning. And when everything is green, you can publish the artifact with a single version, which can version the Docker images, but also all the config map and artifact inside the repository, and push to the deep test repository. So this test repository, when everything is green, is going to just this artifact is going to be used on the non-functional testing and functional testing. So as part of the test, we're going to use the artifact available on test. So we have two phases which are running in parallel, so the functional testing and non-functional testing. So functional testing, so what we are doing is relying heavily on Cilium connectivity test. So we deploy essentially the test suite provided by Cilium, a Cilium project, and then it's essentially some pod talking within each other, and we check like the TNS connectivity, HTTP connectivity, and the right behavior of the Cilium network policies on an existing cluster. And we have our custom additional functional tests, including like making sure namespace network policies can also override the cluster-wide deny policies. We want to restrict the number of identities based on specific labels. So we only allow a specific label defined on the namespaces. And then we make sure like the tenant cannot create too many identities because we are not checking the label on the pod. So when we have a nice number, or we have the expected Cilium identity, which is going to be matching the number of namespaces on the cluster. So we know exactly how many identities we need to target for to be live, and making sure there is no issues. And we want to make sure when we apply some network policies, then it's going to obviously stop the existing TCP connection. So that's one of the tests. And then we've got another test, which is a non-functional testing. And we're trying to have like very short feedback. So you need to run under 30 minutes. And what we want to do, so both of them are fully automated, the functional test and non-functional test. And we want to exercise a full network flow to make sure we reproduce what the tenant are using. So we are going to run some load injector, going to targeting a backend services, and it's going to go through different network paths: internal ingress, external ingresses, and service IP or Kubernetes service. And as part of this path, we're going to use the HTTP and gRPC to rely on the underlying TCP layer to talk to the backend. And obviously, it's going to the load injector is going to resolve Kubernetes domain and through the service IP and core DNS, and which exercise also the UDP path. While we are running this load injection, we're going to include some resilient testing and chaos scenario. So we're going to delete the Cilium agent, etcd member, and the Cilium operator and the backend. And it's really important to delete the backend to make sure we recycle and we exercise the rolling deployment of a dev application, which going to force the load injector to reestablish connection and exercise the load balancing feature of Cilium. So we are trying to simulate with like the worst case scenario. So we target the number of identities, for example, and available on the biggest cluster, and just trying to double it to make sure we can be safe for the next year or two. That's very important when we are trying to test it, to have the existing architecture. Like, for example, we've got Cilium 1.7, and when we want to migrate to 1.9, so we're going to have the existing infrastructure, run the load injection, and then we can deploy 1.9 and making sure like there is no disruption. So we've got a dedicated test for that, for the migration. And obviously, it's hard to catch every single network path and behavior. So we are listening to, and whenever a tenant is reporting an issue, we are just trying to investigate and trying to reproduce it on our test, and adding and relying on regression testing to make sure it's never going to happen again. So as part of those non-functional testing, we've got 4 tests. The first one is identity churn. So we're trying to simulate the identity churn. So we create 5,000 identities and we delete some of them, and then we exercise a Cilium operator garbage collection. And obviously, when you create new identities, because we rely heavily on the cluster entities, the identities are going to inject it inside the BPF map. So we know that there's going to be the worst case scenario. For the first test, obviously, we do the chaos testing, as I said. So we delete all the Cilium operator, etcd member, and backend, and also the Cilium agent. And for now, on our specific environment and on our use cases with the config, we can see a smaller amount of drop only when you restart Cilium agent, and we are investigating why. So we've got a specific and dedicated for that. And we tolerate a few amount of drop, but those drop are just part of the metrics, but we are not seeing it it's not generating any error from the client side or the injector side because of the TCP retry. So we've got the second test, which is exactly the same, but we do not restart Cilium agent and we tolerate 0 drop. The third test is with the identity churn, and we are recreating the Cilium network policies with cluster entity, which means it's going to flush. When you delete a Cilium network policy, flush the BPF map, and it's going to be empty. And when you recreate, it's going to add all the identities available in the cluster inside the BPF map. And the last one is exactly the same, but we don't do identity churn, which means we can isolate which test is going to be, if it's if it's failing due to the identity churn or if it's the Cilium network policy recreation. So to give you a bit more insight, so we've got the test, which is running automated. We rely heavily on the metrics and alert to block and act as a failure test if there is any alert. So you can see at the very top left, you've got the creations rate. So we create some new pod on the new namespaces, which is going to generate and match the identity number. So at peak, we have like 10 pod created. And then you can see we've got like 1,500 pod running on the cluster, which is matching the number of identity event delta, which is changing because we are deleting also at the same time some pods. So you've got the GC exercised. You can see all the BPF map operation, and you can understand what's going on and what Cilium is doing and updating the BPF map. You can see the Cilium drop and any alert, but that's a happy path, so there is no alert. And you can see the 4 tests with the load injection with 2,000 TPS in the middle of the screen. And that's allowing, with the worst case scenario, to making sure we have like the right CPU and memory and defining the CPU and memory for the daemon set before deploying to the production environment. And the last bit is we are checking heavily on the load injector latency, so the 99 percentile, to make sure we don't have any increase in terms of latency and the network path is not affected and we have the right response time. So when both tests are green, that means you've got the second quality gate, and then we are happy to deploy automatically to the extended test. So when it's available on the Docker registry with extended test, every single day at 6 p.m., the extended non-functional testing is going to happen, and it can run up to 16 hours. But for the Cilium case, we are happy with between 6 and 8 hours. So that's giving a good amount of time to load tests and soak tests the behavior of Cilium and making sure there is no memory leak, for example. And we are heavily testing like exactly the same non-functional testing as I've been explaining, the 30-minute one, but for a longer period of time. And we push to the different organizations, so Sky and NBCU for Peacock TV and the Europe Sky Now TV and Sky Go. And we are pushing to pre-dev. So pre-dev, so we've got multiple environments at Sky. We've got pre-dev, dev, stage, and prod. So pre-dev is, so all of them are tenant-facing except pre-dev. So they're not gonna, the tenants are not gonna deploy on it, but only the infrastructure people are gonna deploy some application on top of it. And we monitor every single environment by running continuous load, which is essentially some load injector, which are running continuously load through the internal ingresses, external ingresses, and the Kubernetes services. And with HTTP error on packet drop. And at every single day at 8:30, we're gonna try to check if there is any alert on the previous environment and promote to the next one. So n plus 1 and n plus 2 and etc. Because we have multiple region and multiple cluster, we can stagger the environment and deploy at the beginning at 10 a.m. to the first region and 2 hours later on the region 2 and so on. So thank you. It was a brief overview of what we have been able to do at and deploying at Sky. Cilium.
Thank you, Anthony. And before we jump into questions, I'm going to be cheeky and mention that we are hiring engineers. So if you're interested in finding out more, feel free to get in contact. And with that, we'll open floor to the questions.
All right. Thank you all very much for that presentation. I think that was very useful. I'm joined by Sebastian, Anthony, and Joseph from Sky, and we have some questions from the Slack. So thank you very much. So the first question I have is, CI tests seem to put heavy emphasis on load latency. What eBPF tools are you using to investigate when hitting issues? And that was by Natalia.
Right. So mostly the metrics that have been provided by Cilium and Hubble have been enough for us to investigate the latency issues. The focus has been more on trying to create representative load, a load that's representative of production workloads, and also automate, like fully automating the gating of infrastructure deployments. But apart from that, we've mostly relied on Cilium and Hubble metrics if we're looking at just the latency side. But Anthony, I don't know if you want to add any more around the investigations we did about the Cilium agent itself and its performance.
Yeah, so I think it was mostly like just relying on error and HTTP error and latency from the backend, and relying on the metrics from Cilium agent. Yeah.
Great. Our next question is from Thomas Payne. What fraction of production traffic do you identify as malicious, and how quickly can you drop it?
So the short answer to that is we don't currently use Cilium to do any form of threat detection. We've got a number of other tools at different layers that we use for that.
Awesome. And the next one up is another one by Thomas saying, that's a really impressive set of tests. What sort of production problems have you preemptively solved thanks to this thorough testing?
So it has been helping us a lot to rely on those tests. Like the first one would be like at some point we were relying on CRD, and we've got like a huge number of identities and nodes. And it was very at the beginning of the CRD adoption, because before it was only etcd, dedicated etcd, and we've been like introducing too much load on the API server and etcd, which was like updating basically the status on every single CR, Cilium identities and Cilium endpoint. And then it was adding a lot of fragmentation on the etcd and blowing up the size of the databases, because you need to obviously defragment etcd at some point if you have too many change going through. So that was one which has been catch by our test previously before going to dev and up to production. And another one is, for example, we've been like relying on doing an upgrade from Cilium 1.7 to 1.9, and it has been introducing the Kubernetes service load balancing based on Cilium. And we've been like finding a small race condition where you've got like, you can have some connection reset, when you do rolling deployment and the IP change from the deployment side of it and the pod side of it. So we've been catching it and like reporting the issue and trying to work with Cilium project and contributor to fix it. And so the main issue was using the packet load balancing, but we've been switching to the socket load balancing, which help solving the issue now, and it's actively working on to make sure like this race condition doesn't affect anymore. It was mainly also to make sure like the full platform can scale, because if you have too many identities, you can introduce some at least some load on the BPF map and from the Cilium agent, because it's going to need to inject a lot of identities. So we've been like restricting the number of identities based only on namespace label to make sure like we can scale.
Awesome.
And I guess
very
the last
answer.
one.
Thank you very much.
Yeah, that's fine.
I was thinking, the last question we have is also, do you have any insight into how to leverage eBPF for CI/CD from Natalia?
Right. So I guess the way I would answer that is that, you know, one of the main reasons that we chose Cilium is the fact that it allowed us to decouple teams from each other. So some context for us, we work on a team called Core Engineering. We're responsible for platform as a service. It's a highly multi-tenanted Kubernetes cluster that's used by, you know, over 90 teams. There's over 1,000 engineers using it. And so for us, managing all of those network policies centrally wasn't something that we wanted to do. It's something that we wanted to push down to each of these service teams. But we still had some constraints that need to be managed at a platform level that were our direct constraints as a platforming team. And then we had external stakeholders like the security team or compliance that also wanted to add, you know, their fair share of, you know, requirements on how network policies are managed. And so something like Cilium, as well as, you know, the operators that we're able to build on top of the CRDs that Cilium provide, you know, that's where we can really add that depth of value to our tenants, you know, preserving their autonomy while taking away all of that infrastructure management headache, you know, by centralizing that on this platforming team. So I'd say, you know, we do enable CI/CD for all of our tenants by delegating that responsibility, allowing them to stage these changes, including firewalling changes as they progress through the various environments.
That's an excellent answer. I mean, I know that I've seen more and more teams kind of moving toward a model like this, so that they can unblock people quicker and move things forward. Thank you, gentlemen, so much for your presentation and for answering these questions. There's a couple more in the thread. Please jump in and answer those questions. And over to you, Liz.
Thanks, Duffy, and thank you to the team from Sky. So we're about to talk about something that isn't Linux. We're going to talk about eBPF for Windows. And joining us to present is the last keynote of today is Dave Thaler from Microsoft.
Hello, everyone. I'm Dave Thaler. I'm an engineer at Microsoft, and I work on open source and standards. And today we're going to talk about eBPF for Windows. Now, Microsoft does a lot of different things that relate to eBPF in some way, right? And so we came to the eBPF Summit last year, which was great. And we heard even in the audience, there were audience questions to the presenters saying, so when can we get eBPF for Windows? Right? We'd already been thinking about doing this because we've been hearing the same questions ourselves. And so that just gave us confidence that says, okay, maybe the community will really want us to do this. And so that's when we started this initiative that we're going to talk about today. So there's a couple different things that are properties of eBPF that are really attractive that we don't already have really in the Windows world. So the first one has to do with flexibility, right? We have APIs such as the Windows filtering platform, which is what people use to develop firewalls and filter drivers. Drivers are the equivalent of Linux kernel modules that you use to extend the kernel by writing code. And the things like the APIs we have today have sort of fixed schemas, right? Like 5 tuples and so forth. We can't necessarily do arbitrary things. And so the flexibility eBPF provides, where you can have the package.
How's my mic doing
set
right
of,
now?
helpers and stuff that you can do relatively arbitrary things. So subject to whatever the verifier has lets you do. So that's an attractive property to many people. Second one is that when somebody writes a driver, the way that it works is you send it off to Microsoft to get signed, right? Because the kernel is not going to load it unless it carries a Microsoft signature. So you got to send your driver off to Microsoft to get signed. And that extra delay is not always desirable if you're just trying to extend something in the kernel for observability or DOS protection or whatever. And so this notion that says, how do I write some code, get it verified and JITted, and put it into execution right now without having to wait? Okay. And the last one is that the whole notion of the safety properties that the verifier provides is often much stronger than the types of tests and things that Microsoft will run before signing somebody else's driver. So you can say, well, if I run it through this verifier, then I can get a stronger level of reliability and security confidence. Okay? So all these are very attractive properties that customers have said, can we get eBPF for Windows for these reasons? So we said, okay, let's see what we can do here.
Do I need to
We put together this project with an architecture that we tried to keep as similar as possible to the architecture that we're all familiar with on Linux. Okay? Now, Windows itself has some unique properties there that we'll talk about there. So we can say, spot the differences between the next two pictures, right? So here's our classic Linux picture with tool chains like BCC. We have libraries like eBPF, and you have things that exist in the kernel where your verifier and your JIT compiler and interpreter and so on are. And you have components like TCP/IP stack, et cetera, that expose eBPF hooks and helpers. Okay, so let's go forward to the eBPF for Windows version of this slide. So here we go. There's a couple things that you'll notice that are different. Okay, so first of all, let me talk about the key. What's the color coding here? Okay, straight blue is things that are unchanged from Windows. Okay, because we want this to work without having to change Windows. If people already have Windows deployed, how do they want eBPF now for the Windows they already have without having to wait for a future version of Windows? Okay, so the blue is unchanged Windows components. So we said all of this is on Windows, not in Windows. Okay, so you've already got Windows and you install on there eBPF on top of existing Windows. Okay, so that's the blue. And so how do we do that? And we'll talk about that. That's the shim that we'll get back to. Okay. Otherwise, all of the green components are regular open source projects. So one of our goals was to say, we don't want to reinvent anything. We want to reuse as much as possible so that we're all using common code for things like, eBPF and BCC and so on. Okay. So all the dark green is open source projects that already exist that we just want to run on top of Windows. Okay. Some of them they have to participate in to make sure they can get compiled on Windows if they were compiled to be Linux only or whatever in the CMake files or whatever they're using. Okay? So you have to work with them. But the point is the light green is the hosting infrastructure. How do you make that map to the Windows internals? Like how do you compile as a Windows driver? How do you make a Windows syscall? Right, that sort of thing. How do you compile as a Windows library or host a service, that type of thing? And so that's what the light green is intended to be. Okay. Now, let me talk a bit about maybe the libbpf in the middle, which is one that is kind of the next step here, because we've got the verifier, the JIT compiler, the interpreter, and so on that work great, the same on Windows and other platforms. libbpf is one that we still got to work with, where that one has a bunch of Linux-specific code, where the goal is to factor that into parts that are cross-platform versus the parts that are inherently specific to the platform. Like today, libbpf tends to combine those two. They have the cross-platform, the generic libbpf code, plus how do I actually call the Linux syscall, BPF syscall, that kind of thing. And we really want to factor those such that the bottom part there, that light green lib, is the how do you call the Windows-specific code underneath the covers while still keeping all of the business logic of libbpf on top. And so that's why you see this little split there as to where we want libbpf to evolve. Okay. Another example, I'll get to this on the next slide, which is the verifier and the jitter. We have those running up in user mode or user land. And then the last piece that I'll talk about now is where you see the eBPF shim in the bottom middle. So I mentioned the way that you extend the Windows kernels by writing a driver, right? Both the execution context driver, the light green box on the bottom right, as well as the eBPF shim are drivers on Windows, okay? So the eBPF shim, we have a driver that's in the project right now that consumes on the left the public Windows APIs exposed by existing versions of Windows. And on the right, it translates those into eBPF hooks and helpers that we know, okay? And so it's the shim that sits in between those, and that gets installed as a driver. This actually has two different colors because the one that we have in the project right now is all open source in the project and it sits on top of public APIs, right? But somebody could do the same thing and put an eBPF shim on any driver that somebody wants to do. So even somebody's private driver that exposes private APIs, if you got your own Windows driver right now, you could have your own eBPF shim for it. Or in the future, there could be drivers that expose eBPF hooks and helpers directly without having to have a shim. That's kind of the ideal world that we want to get to, right? But in the meantime, we want anybody to wait, and so hence the shim idea, okay? And we can have multiple of these, and that's why there's kind of both colors there, because you could have one shim that calls some agents that sits for some hooks and helpers, and another shim for other ones. Okay. And so a lot of variety here, and I'll talk more about why that's a separate driver from the execution context, although some of it may be obvious now. All right, let's keep going. Okay, so let's talk more about why the verifier and the jitter, we put those in user mode. Well, one reason, I guess, just during development, you get better reliability and security. It's easier to debug stuff if it's running up in user mode instead of in the kernel. But, security aspect is that, some security people have argued that if you put the verifier and the jitter in a different address space from the kernel itself, then things like side channel attacks, Spectre and so on, start to become a lot harder, less ability to expose kernel secrets and so on. But probably the first reason that we did it was again because we wanted to reuse existing projects, right? We found existing projects like eBPF and Prevail and so on that already had ready-made libraries for doing jitting, verification, and so on, that were easy to make work up in user mode libraries, but were really hard to make work in the Windows kernel. Okay. So by putting stuff in user mode, then that meant, hey, less work for us to do. We can get stuff up and running and use it now, right, without having to wait. However, we think it's also a good building block. We'll probably want to keep it there, right, for a couple of reasons. So one is we aspire to have hooks and helpers exposed not just from the kernel, but from things like user mode daemons or Windows services, that type of thing. And so you can have some programs attached to the kernel. You can have some eBPF programs attached to, say, a user mode service. And how do we do that with the same verification and jitting libraries? Well, we think that the architecture we have is one that will naturally lend itself to doing that on Windows. Okay. And so this notion of wanting to run, say, the jitter up in user mode is the same desire as like the eBPF project has. So there's this nice synergy between projects that let us work together with other projects, which has been great. So our goal for these building blocks, the jitter, interpreter, verifier, and so on, is we want them to be cross-platform, to work on Linux, Windows, anything else, okay, and context agile. And what I mean by that is that the library itself, the code is not written to be kernel code or userland code. It's just written to be code that can be linked either way. Okay? And that allows use of many different contexts, right? We've experimented with stuff inside like an SGX enclave and so on. And so the more different context agile it is, the more reusable it is, the better it is for all of us, because now we're focusing the community efforts all on one code base or a small number of code bases rather than fragmenting across one for every platform. So that means that our goal for the eBPF for Windows project is that this repository should really only have code in it that's inherently Windows specific. Right? How do you actually compile an actual Windows driver, right? How do you actually make the underlying Windows system call, right? How do you reference count a Windows object? What's the relationship to the Windows file system, which is different from how the Linux file system works and so on, right? The file system subsystem. And so how do you have that mapping there underneath the covers? And that's the code that's really meant to be in this repository. Everything else is like core business logic. We'd rather keep it out of this repository and keep that in other cross-platform projects. It's not specific to Windows, and just work with those. Okay. Some of those I mentioned, we've done that already between the interpreter, the jitter, and the verifier. Some of the ones there's still work that needs to be done, such as in libEPF is an example of one that we want to, is kind of the next big step to do. So, all right, let's keep going here. So let's talk more about security, right? Because people have asked us, when can I actually run the thing, right? And the point is that I mentioned that the Windows kernel will only load code that gets signed for production, okay? Well, that's not going to happen until the security hardening work is done. Until then, you can run demos in the test signing mode, and you're just not going to run it in production, but you can make the demo, but it's not necessarily secure. We got to get the security hardening done, okay? And this is something that's not going to happen overnight. We started the project early, because we want this to be done as part of a community effort. Okay? And so there's an active work going on in these areas. We've experimented with at least 2 different ways of having that little secure environment up in user mode to be able to host the jitter and the verifier. We've tried it inside, say, an SGX enclave, but that has a hardware dependency, and we want solutions that can run on any hardware, right? And so we're experimenting with a couple different approaches. There's active design work going on in this area. We would love to have more collaborators in this particular area. And if you're interested in more, you can ask me about it or come to our meetings that I'll talk about at the end. But one key difference between Windows and some other scenarios is that in a Windows world, you have things like the Windows hypervisor that if you turn it on, then there's a technology called HVCI, Hypervisor Enforced Code Integrity, that say that even if you get root on the machine, you're running as administrator, you still can't inject code into the kernel. Okay? The hypervisor is providing that enforcement. Okay? And so that means that there's a security distinction where there's an elevation of privilege attack in between those. Okay? That means that things like your JITted code path is actually not directly possible without having to get stuff signed by a signature that the hypervisor will trust, not just the kernel, but the hypervisor has to trust it. Okay? So this is actually this different security model that the Windows hypervisor has. Okay? And this causes impact on us in the security hardening for Windows because we don't want to degrade that promise either. Right? And so today the status in the project is that interpreted mode works with HVCI on. When HVCI is off, both interpreted and JITted mode work. Okay? So again, this is an area of active design work. Love to collaborate with any of you in the community that want to participate in this. Okay, so one of our core principles in doing the project is that we wanted eBPF to be easy to extend. Right? There's lots of hooks and helpers and things that people are familiar with in the eBPF industry. We've only just started, right? There's only a couple that we've started putting in the project already. We want to make it easy for other people to add them, even people to add them after, outside of the project itself, right? You want to add a hook or a helper for your own subsystem or your own driver for Windows or whatever. How do we make that be easy? So these are our goals for the project, that in order to add a hook or helper, you should not need to recompile Windows, certainly, because you want to work with existing Windows. You shouldn't even need to recompile the eBPF for Windows project. And in particular, you shouldn't need to recompile the verifier or the jitter, and you shouldn't even need to reboot, okay, to add a new hook or helper. And so to go along with that, kind of the corollary is because you can do all that without rebooting, then that means that there's this need for any user, developer, whatever, to be able to query the runtime to say, what is actually installed here? Which program types do I have? What helper functions are available on this system, right? So all this is made possible with a runtime introspection mechanism. And so hooks and helpers are added via new extension drivers, right? And that was that eBPF shim piece that I talked about before that's separate from the runtime, which was the execution context box on the bottom right. So you can add a new extension driver at any time. The extension driver is what implements the hooks or helpers, okay? And then the hooks and helpers are then provided metadata. The extension provides the metadata about them to the runtime itself, so that the other components, the verifier, the jitter, and so on, can query the metadata and then act on the metadata as being data-driven, right? So the verifier, for example, doesn't have any prototypes hard-coded, right? It queries them at runtime, gets them from the execution context, and then operates on the prototypes and so on for verification purposes. So all this means that it can be done without having to embed knowledge of these things in these other components, okay? This is a building block that actually allows other things in the future, like we want to allow other execution contexts to be added at runtime, like new services that come up that can attach programs to. Or I want to allow my verification to be done off machine and use signed programs, right? We're very interested in this notion of signed eBPF programs that's been talked about in a couple of places. I think this is a great approach that we would love to be able to leverage, even on the Windows project here. And so we're trying to design to make that be possible in the future. So with that, let me just thank everybody for your participation. We have the link to our repo here. We have weekly office hours. We have a Zoom meeting basically every Monday morning. The link there is in the GitHub. We would love to have additional contributors. We just go over open issues, pull requests, whatever it is that people want to discuss, at least triage all new issues. If you file an issue, you have a feature request for us, feel free to file an issue. If you want to contribute, that'd be lovely. We would love to have more contributors. We use, help wanted and good first issue, and we triage issues. So it'd be really easy if somebody else is interested in the project and wants to contribute into this project. But otherwise, we'd love to continue collaborating with the other building block pieces that I mentioned. We've seen great efforts across the community right now, and love to see that continue. So thanks for listening, and happy to take any questions now.
Thank you so much for that talk, Dave. It's really fascinating that eBPF is a thing on Windows now. So we've got quite a few questions came in for you. One of them is from Mercio asking about the relationship between Linux and Windows eBPF verifiers, and would it make sense to have a common verifier for the different operating systems?
So this notion of having a common verifier across multiple OSs is a really interesting idea that we would love to do. When we start off this project, we couldn't directly use the Linux verifier as is. We were not able to use that one directly because it was too tied and embedded into the Linux kernel itself. And so we had to look around elsewhere, and we were able to find the Prevail project. The Prevail project is intended to be cross-platform. Sorry, I'm getting a bit of crosstalk myself here, so sorry about that.
Okay. So well, I appreciate you've got some audio issues, but let's see if we can take another couple of questions. So what would prevent someone from using a malicious verifier in user space rather than the one you intended them to use?
So I alluded to this one a little bit in the slide on security hardening. And so the point is that the verifier and the JIT compiler have to run in what was labeled a secure environment, right? And that secure environment has to be locked down so that you can't specifically do this particular attack, right? And so the whole point is to prevent the attack that Nathan, that you're calling out here. Okay? And we've looked at a couple of different ways of doing that. Okay. We've experimented with using, say, an SGX enclave, but of course that requires hardware, special hardware, and we want something that can really run anywhere, right? And so we're looking at doing things like, okay, can you run it in user mode in a special VM, a separate VTL, and it's the hypervisor that provides the isolation there. And so the point is that you can't just run a regular user mode process because you can't inject stuff into the secure environment, right? So the point is it really is a security boundary that is as trusted as the kernel. We're still experimenting with a couple of different ways to do that. We might be able to find something better in the future. We've got a couple ideas right now, and we would love to have others that want to collaborate on this idea. But the point is it's not just a regular user space process, right?
Got it. And do you think that the Linux BPF implementation could benefit from some of this work that you've been doing on security hardening in Windows, or is that work very specific to Windows?
I think there's a little bit of each. I mean, when we started this project, we tried to make it be a community project where we went open source very early, right? So in other words, it's not something that is ready for production yet because we wanted to do this together with the community. And so I think there's a bunch of interesting directions we've been discussing with other people in the industry as kind of a collaborative effort, whether it's, across Windows and Linux and so on. So we're very interested in notions of things like, can you use signed code? Can you take your verifier? Can you even run your verifier on a different machine, right? Can you do that with signed code? And so there's a lot of things that we're interested in doing that actually overlap with other projects. So we're working together with other members of the community on this. And so we see it as really the part that's in the eBPF for Windows project is the stuff that's really inherently about Windows, right? The stuff that is really, what is it really that's a Windows driver? What's this? How does it interact with the Windows security model itself? Any of the things that are differences. Things that are really just, standard features for OSs should really be shareable across things. And so I imagine that there's going to be lots of opportunity to share technologies back and forward across Linux and Windows, especially since, in my group at Microsoft, we do both Windows and Linux. And so we look for things that are specifically cross-plat as kind of our goal. So as much as possible, but there's going to be some things that are just very specific to the way that Windows does things. And that's the example that I gave on the slide a couple slides back was the HVCI notion in Windows is kind of unique. So,
and you'd probably be pleased to hear there's quite a lot of folks in Slack interested in the idea of Microsoft contributing an eBPF CTF challenge on Windows for next year's summit. So that's a challenge for you.
Yeah, I love that idea. So I guess the best I could say is challenge accepted. I mean, what I would actually love to see is I'd actually love to see a CTF that would be cross-platform. That would be my ideal world, right? Where you could try it on any version of Linux or a version of Windows or whatever and run the same CTF. I don't know if that's possible, but that would be a challenge to put out there. And anyone wants to collaborate on that, love to collaborate. So coming up with one.
I think that's a fabulous idea, isn't it? Right. So thank you so much for your time today, Dave, and sharing all this experience about eBPF on Windows. It's really an exciting development. And I'm going to hand back now to Duffy.
Thank you, Liz and Dave. That was tremendous. And now we're going to transition into some lightning talks on the same subject, deploying Kubernetes deploying eBPF inside of Kubernetes. The first one will be from Matthew Leonard from ContainerIQ, talking about getting started deploying and running
Hi, I'm Matt Lenhard, and today I'm going to walk you through getting started deploying and running BCC in your Kubernetes cluster, as well as some of the lessons I've learned and mistakes I've made along the way. I've also set up an example repo that has a sample BCC application that you can modify and have it phone home or maybe ping some other application. It also has all of the necessary Docker files and Kubernetes deployment file that you'll need to get up and running. So the first step is to set up the init container. And what the init container is going to do is it's going to install the necessary Linux headers onto all of your nodes. And since we're running this as a daemon set, it will automatically install the necessary headers onto any new node that you add into your application. I also wanted to give a shout out to the kubectl trace team for putting together a simple bash script that will grab the current Linux kernel version and install the necessary Linux headers package to match that version. I've tested this out across GKE, AKS, EKS, and just vanilla Kubernetes installs through like kops, and it's worked every time. It's really an awesome script, so shout out to them. The next step is to set up the necessary BCC container. That's where you're actually going to run the BCC application from. You could run one of their tools or modify it to your own custom application. Like I said earlier, maybe you want to phone home and do some data analysis from what you found. But yeah, it's pretty simple. You're going to install like the necessary packages to get everything up and running, and then you're going to build BCC from source. And then at the bottom there, we're just running the file through Python interpreter. If you wanted to extend this a little bit, you could copy the files over to something smaller than Ubuntu, maybe like Alpine or another image source. The next step is setting up the Kubernetes deployment or the YAML file you're going to use to deploy this. So there's a few key things to get started. We're going to run this as a daemon set so that it automatically instruments any new node you add to the cluster. You're going to need to run the container as privileged. If you are using a newer kernel version, you might be able to just add the eBPF capability. I haven't tested this yet because unfortunately I'm stuck using 4.3, but on newer kernel versions, the eBPF capability should work. Finally, you're going to have the two main containers I talked about earlier, the init container to install the Linux headers and the BCC container to run BCC or your own custom tool. So something that's super important is making sure you set the necessary resource requests. Something that I ran into personally is I didn't set an ephemeral storage request when I was first testing this on like a test cluster I had. And when I installed the Linux headers, it ended up eating up all of the ephemeral storage on the node. This caused a bunch of pod evictions and like some cascading failures from there. Luckily, it's just a test cluster, so it wasn't that big of a deal, but definitely something you should be setting when you're running this tool. You're also going to want to make sure you mount the proper volumes. As you can see, the ones at the top are for the installation of the Linux headers. That's basically going to be used to grab your kernel version. At the bottom, we're also mounting the modules so that the BCC tool will run as expected. Yeah, and that's it. It's pretty straightforward to get up and running with BCC in Kubernetes. Please check out the repo I have set up. You can get started with this super easily, modify the tool to do anything you want. And there's a bunch of cool applications in BCC you can use to analyze your Kubernetes cluster. Finally, I want to give a shout out to kubectl trace for putting together that Linux headers installation script, as well as BCC for putting together a ton of awesome tools and making it really easy to utilize eBPF. Thanks for watching, and please let me know if you have any questions.
Thank you very much, Matt, for that incredible talk. Those of you in the thread will be able to see the GitHub repository that Matt linked. Our next talk is Scheduling BPF on Kubernetes Doesn't Have to Be Difficult by my good friend Leonardo Donato.
Hello, everybody. I'm Leo. 5 minutes only, so I'm gonna be as fast as I can, almost like Jacobs. I guess you already know that kubectl trace is a kubectl plugin, right? It was created by me and my friend Lorenzo about 3 years ago. At that time, we needed a way to easily schedule BPF trace programs on our Kubernetes clusters in minutes. I'm assuming also that everyone here knows what BPF trace is, right? Just to be sure everybody is on track, let's just say it's a high-level tracing language that compiles nice one-liners to eBPF so that you are up and running in a snap. Well, kubectl trace grown a lot over time. In fact, as of today, the version of master, it's also able to schedule different types of tracing programs that compile to eBPF. For example, the famous BCC programs. Ending a new arbitrary tracer is easy, and this maybe is a topic for another talk. We'll accept it as long as it respects the existing interface for system and process tracing that kubectl trace provides, so node level or process level, and it does not bloat the size of our trace runner image. But now it's demo time, clock is ticking, may the demo gods help us. I guess I got no time for showing you how to install kubectl trace. All you need to know is that you can install it via Crew, or you can install it using Go modules, or even better, install it from source with make build. Once you got it, just type trace, get a sense of what you can do with it. Clearly, you can run trace programs with run subcommand. Attached to them, take a look at the output. You can even instruct it to upload the output. Then you can get the trace jobs running on your cluster with the get subcommand, and finally you can delete them. A very Kubernetes-like interface. For this demo, I'm also assuming you already have a Kubernetes cluster that just works, similar to this one with 3 nodes that I set up, and with various workloads deployed on it, especially with very cool app like Saturday. A nice app that shows Kitty. Let me show it to you. As you can see, there's a render here. Every time we refresh the page, it shows another cool Kitty and increments the render. We're gonna now trace function, counter value, without modifying the code. Okay, we like to go look under the hoods. To do so, we're gonna define a Linux UREF probe, a Linux kernel feature that instruments the end and the return value of a function. Let's see how to do it with kubectl trace against our running Saturday in our running Kubernetes cluster. So we want to run a BPF trace program that instruments the Saturday binary proc container DX with a NuRet probe on the counter value function, which returns the return value. We specify the Kubernetes resource, the pod, the namespace too. We tell it that we want to attach to the trace job, and we specify the fetch headers flag that instructs kubectl trace to decorate the job with an int sidecar responsible of downloading the correct kernel headers to get the BPF trace program to compile and to actually work. Created. Now we want to quickly check the trace job is running, and it is. Let's request the Saturday homepage from here. Count 67. Ashy kittens, I'm done. That's enough. Let's do it again. 68, and the counter matches because that's the return value. Hey, it works. Look at the counter. While I delete the previous trace job, let me tell you that recently, together with BCC and Ruby Spy traces, we also introduced a feature to select by deployment, which targets the first valid pod within it and then uses the existing pod processing logic from there. Or even better, we introduced a new flag called process selector, target a specific process to trace. I gotta leave this experimentation as homeworks to you, otherwise I guess I'm gonna be over time. Let's just quickly trace directory on our NAS node. For example, we may want to use BPF trace point to count all the syscalls entering on our nodes. Wait, I changed my mind. Even better, we may want to focus on the exact family syscalls because we're paranoid and for reasons. We want to print all of them. Trace created. Look, things happening here, things executing. Cool, isn't it? As we've seen, scheduling various kinds of BPF programs on Kubernetes is easy with kubectl trace, and we're working to make it even easier and support different tracers. Feel free to join us in the kubectl trace channel over the Kubernetes Slack, open issues, ask questions, ping me over Twitter, and then maybe even contribute some new traces to this amazing tool. We would like it. Thank you, everyone. Ciao.
Well, that was quite the day. I know that I've learned a ton. It was great to see all of the interactivity in the Slack. So thank you for all of your questions, and thanks for keeping it so interactive all day long.
Absolutely. And thank you so much for the brilliant pictures of bees. Let's bring up a few that we had time to put into a slide today. So one of those is even a piñata, I think. It's amazing. There are some more pictures that we will post tomorrow. Go ahead, Tuffy.
One of my favorite bee pictures, I have to say, was of the bee cookie that you had earlier this morning, kind of being eaten throughout the day.
Yeah, I've eaten its head off. Yeah. So tomorrow we're going to have some more fantastic sessions for you. The themes of the day are going to be around networking, and then about writing eBPF programs yourself. And then we've got some advanced topics for the experts amongst us. As always, you will find all the details on that Sessionize mobile site that you can mark your favorites in.
And just like today, we did have a live solving session with Tabitha Sable for Challenge 1. Tomorrow we'll do the same. And Challenge 2 has already been published. So if you haven't checked it out, definitely check it out and see how far you get. It's an incredible thing.
Yeah, that Capture the Flag session was brilliant. I'm really looking forward to the next one tomorrow. So don't forget, we want your feedback in the survey that you'll find pinned in the Slack channel. And if you've been enjoying your time today, as they say, tell your friends. Bring your friends along tomorrow. Tell them about it on social media. We've been using the hashtag eBPF Summit. So yeah, we're hoping that you'll bring all your friends for more fantastic eBPF content tomorrow.
Indeed. Thank you so much, everyone. And I will see you tomorrow morning.
And I will see you tomorrow afternoon, London time. See you then.